So here's where we're really at. Unit 2 is about the top end, so the cylinder head, which will include valves, cams, intake ports, how the valves are actuated, so push rods or rocker arms or lifters or all that type of stuff. And additionally, timing, which is timing chains, timing belts, VVT, also variable valve timing is in this one. And then also induction, which is really more induction and exhaust. So how the engine breathes, how the intakes are designed, how the exhaust is designed. And also, fun one, that includes turbochargers, superchargers, which also includes bypass valve, wastegates, blow-off valves, all that type of stuff. So um, this we're going to cover a whole bunch of different stuff, not just the top end, but those land best in here. So that's where they're included. So without any further delay, starting with the camshaft, we've talked about it a bit, but we'll summarize it again. The purpose of the camshaft is it has these lobes, which you can see, and each of those lobes is going to provide a motion, right? So if this lobe is the intake valve and this lobe is the exhaust valve, this lobe is going to open the intake valve and this lobe is going to open the exhaust valve. And that's its purpose. And typically the way that we'll do it, um, we could do a single cam, we could do the single overhead cam, we could do the single cam and block, we could do a dual overhead cam. But if you do a dual overhead cam and it's a V engine like a V6 or V8, you end up with two heads with two cams. So you actually end up with four, but we don't really call it a four cam. We just call it a dual overhead cam V6 or something. So there could be a number of different camshafts. A word to recognize here is eccentrics. So when we did suspension, you remember we use the term eccentric. The eccentric is the cam lobe. So it's eccentric, meaning it's not just centered. It's not just round. It's almost like an oval shape. It's oblonged. So the eccentric that can move a control arm on a suspension is also kind of like an eccentric that can open a valve, actuate a valve on an engine. Cool. So those are the lobes. As you look, when we're measuring the cam, this is one of the primary measurements we're going to do. We would use a micrometer. We could measure in different directions. We could be measuring the journals. So this is actually a journal. It may ride on a bearing, like if it's cam and block, an OHV engine, that camshaft is slid into the block and it's definitely going to be riding on bearings. But if it's an overhead cam, um, it may or may not. So if it's like an iron block, it's going to have bearings. But if it's an aluminum, if it's an iron head, it's going to have bearings. If it's an aluminum head, well, a lot of those don't have bearings. They just literally have the cam riding in the aluminum because the aluminum's already pretty soft and they just precision machine it. So if we were to, let's say, have wear on this journal, that would mean it's going to end up loose in the bearings or in the saddles if it has no bearings. And that's going to cause oil pressure issues. That could cause us several different problems. It could move around, some issues there. So when we go to really check it out, you'll have to actually measure those journals. You can also be measuring those journals for add around. I don't know how likely that is, but you could be measuring for wear and add around. Now, the other picture here on the right is totally different. On this one, we're measuring the camshaft lobe. And we talk about it a lot from like a performance standpoint, like, oh, let me measure my camshaft lobe. And if you measure the base circle, which is coming up, and the lobe, you can actually measure how much lift it has, which is like, oh, this is a high performance cam, or this is the stock cam. But the other thing is, it's not real common, but it does happen. The camshaft lobes can wear. So if you have an issue with a lifter, like let's say it's a roller lifter, and the little roller's bearing is seized up and you got that roller lifter dragging across the surface of the cam, or there's even been times where the roller lifters will spin sideways on their bore, they will wear a cam out. And the top of that lobe maybe should be 600 thousandths higher than the base circle. Well, it'll wear it down 600 to 500 to 300 to 200. It might even wear it full round. If it were to wear it full round, what would the effect be? Just think about that. If it wears a full round, does it do any lifting? It doesn't do any
No.
action, right? Exactly. So the second that cam lobe is starting to wear, you're getting less valve actuation. So on a rebuild, we need to measure this. But it could go another way too. Like I actually have a machine behind me back here. It's a Polaris. And I've had it for a long time. It's old. And just slowly over time, it was losing power, losing power, losing power. And then it got to the point where it really couldn't make it up the hill if I was trying to tow my little trailer with trash cans in it. I'm like, what is wrong with this thing? And I was really looking at the carburetor, and fuel and see, like, is the fuel pump not moving enough volume? Is the exhaust restricted? These types of things we see more. Is the intake clear, or maybe the air filter is extremely clogged? And all that looked good. So it was a little bit of a head scratcher. And what it ended up actually being, I had to get really deep in the engine, and I noticed it failed the compression test. It didn't really make much compression. So at first, I thought the engine was just kind of worn out. It's 25 years old. It's hammered. But I did a little bit more of a test, right? I compression tested it. It didn't build a lot of compression. But then I did a cylinder leakage test, expecting for it to be leaking past the rings, just to have a worn out cylinder, worn out piston, worn out rings. And actually, it was pretty sealed. I'm thinking, like, if the cylinder's sealed, but it's not making much compression, that's again a head scratcher. If the valves aren't opening all the way, it's not going to pull a lot of air in. It's going to pull in less air, which means it's going to make less compression, which means it's going to have less power, which means I'm not going to make it up the hill with the trash cans. So I had to perform some extensive diagnosis and ultimately ended up pulling the cam out of it and measuring the lobes and the exhaust lobe. I actually don't remember if it was the intake or exhaust. I believe it was the exhaust lobe severely worn, like worn half. So it was opening the valve, but it was not opening the valve all the way. It was only opening the valve halfway. So it was a really crazy issue that I experienced on that. I've seen that in another few cars too. We had a couple of like 5.3 or 6 liters with some worn cam lobes. It's rare, but it can happen. And that's how you'd actually measure it, right? You probably wouldn't measure it first, though. You do some testing, and if it indicates the cylinder is not making good compression, but it's holding the air on a cylinder leakage test, you may check the cam, right? So
Wait, so if they are worn, are we replacing them or are we doing machining?
Good question. So let me back up. The lobe right here was worn, but something rides against the lobe. So if the lobe is worn, whatever the lobe rides against is going to be worn too. So like in my case, the rocker arm on that Polaris was totally worn. So I did a cam and a rocker arm, good to go. On the 5.3s on the LS engines, the roller lifter rides on the cam, and the roller lifter is held by a little retainer. So those needed a cam, a roller lifter, which you probably really would do the set, right? Because you're doing a new cam, and all the roller lifters ride on the cam. So, and it's a big job. So all the lifters were replaced, and then also the retainer. Actually, one of the retainers had broken, and that's what allowed the lifter to turn. So no, it's just a matter of what else is worn, but we don't necessarily have to do machining because the cam lobes don't sit in the bearing or the saddle or the block or the head or anything. They're really more actuating the valve train parts. Now, if you had a messed up cam journal that rides in the head, it's going to have probably messed the head up, at which point, depending on the head, if it's got bearings, you might just be able to do bearings. But if it doesn't have bearings, it probably actually would have ruined the cylinder head itself. And so depends on where the wear is. Okay, good. Now, when we talk about the camshaft, some cams could be potentially bent. We could lay it in these things called V blocks. The V blocks are just going to support it on the journals, and you could put a dial indicator on this journal right here. P.S. ASE concept right here. You could put a dial indicator on this journal, and you could spin it. and you should get no run out. Because if it's round and it's not bent, there shouldn't be any run out. If you're getting run out on this, it's not likely because your cam journal is like out around because it's been spinning its whole life. How the heck would it end up out around? It's actually more likely that the camshaft got bent. Why'd the camshaft get bent? It actually may have been technician error. They may have unbolted it. There's typically a procedure on how to unbolt the cams. If you, let's just say the procedure is to remove the two outside caps and then remove this one and then remove this one, but instead you just unbolt them from one side. When you unbolt one side, the valve springs try to lift that cam up, and that cam is under a lot of stress. You can break a cam too. I'd actually say it might be more likely to break a cam than bend a cam, but there's a possibility to bend a cam. So if the pointer of the dial indicator is on this big part right there, that's the journal. We're measuring for like out around or to have a bent camshaft. However, big difference if that pointer of the dial indicator is on the lobe, we know the lobes are out around. That's how they work. They're eccentric on purpose. All right. So if we were to have the dial indicator on the lobe, what we'd actually do is set the dial indicator to 0 on the base circle, and then you turn it. And the second it comes off of 0, that means it's starting to ramp. And that's one way that we can measure the lift, is we can see how many thousandths of an inch above 0 it goes. That would tell us our lift of the cam. But also, the second it starts to ramp, that begins the duration time of the cam. So how long is the valve open? Second it comes off of 0, second it comes off that base circle, we'd make a mark, and then we'd measure in degrees how long it takes to get all the way open and then all the way back to 0 to be closed. And then you'd record that in degrees. That would give you the duration. Would you really do that in service? Probably not. But you got to understand that as a concept for how the cam is made, right? So measure in the journal, add around or bent, measure in the lobe, lift or duration. Okay. You got to be able to see where that pointer is, and that tells you what we're measuring. And so again, here's measuring the lobe with the dial indicator, like we kind of talked about. It's out of round measurement. So like a drum, like what we talked about in unit 1 is, you're going to measure this direction. Maybe we call this 3 and 9, if you will. And then you're also going to measure at 12 and 6. And if there's a difference, that's telling you out around. Cool. And then here's that lobe. So this right here, you can see is measuring the largest diameter across the lobe. That would be like the max. Then you would do this at more like 12 and 6, and that would be more like the base circle. And the difference between the two will tell you just how out of round it is, but not in a bad way, because we're not measuring the journal, we're measuring the lobe. We need it out of round, right? So it's not really that complicated if you think about it. Here's showing the base circle, and there's the lobe, right? We're measuring the same part, but in this direction, we're not measuring really how eccentric the lobe is, but in this direction, we are. Cool. Pretty simple. All right. And then in service info, it may call out your bearing, your journal diameter could be, between this and this. And if it's under that, that means the cam is worn, which means we're replacing it. And sometimes they can vary. Now, this is for the cam. And then if you look just below, this says bearing inside diameter, journals 1 and 4. That's an inside diameter measurement, right? So the first one is the cam being measured like this. We're measuring it like that. The second measurement, is using a T gauge and measuring the hole, or using an internal micrometer or a dial bore gauge. We're measuring the actual hole. So now if you think about it for a quick second, and I would actually like to make this a little bit more round numbers. Okay. So some of those numbers are a little tricky. So let me do a quick annotate. Just 1 second, annotate, and I got to get the marker. It's kind of weird. I picked annotate, but I didn't get my toolbar pulled up. Annotate. Okay, bummer. Weird. Why are you making me mad? Annotate usually pops up a bar. Let me kill share for a quick second. Okay, let me click that. Actually, looks like the share is working. Hmm. Okay. You'll have to just follow what I'm saying because for some reason I'm not getting my toolbar, which is really weird. Never had that happen. Okay, if we did this measurement, let's make the bearing diameter a round number 50. The bearing diameter is 50. If the journal diameter is 49, how much clearance is there? If it's 50 millimeters and 50 millimeters and 49 millimeters.
1 millimeter clearance.
I gave the answer away too, but you guys can do that math, right? All I want you to understand is the concept. What the math is, I don't really know. It would depend on the measurement. If it was really like, hey, your bearing diameter is this number, that would be totally different. So if you have the bearing diameter on the inside and you have the cam journal diameter, you can tell how much smaller the cam is going to be than the bearing. The cam needs to be smaller than the bearing. Okay, so these numbers are just samples, but the cam journal would need to be smaller than the bearing because it needs to go in there and it needs to have a little clearance so that it can have some room for oil. If you were to measure that and it were to not have enough oil clearance, like it were to have basically nothing, you had like 0 thousandths of an inch, you don't have any room for oil. What do you think is going to happen to that bearing and journal?
Gonna get all messed up and scored up.
It's going to get nuked. We need the oil in there. We need those parts to ride on a thin film of oil, and those are pressurized by the oil pump. And if we don't have room for the oil won't go there. It'll be like basically a dry metal running over a dry bearing. It's going to chew itself up. So that's one of the things that we measure on our cylinder head in our overhaul is the journal clearance. Now there's another way to do it, and actually it's going to come up later. Okay, but if you understood the concept, when I show it later, you'd be like, oh yeah, I got it. Cool. So this talked about a little bit more about how we calculate the lobe lift, which I think you got, right? Right here, from let's say 9 to 3, we're measuring what we call the base circle. You can see the base circle is the perfect circle here. We get the baseline of the base circle, and let's just say that is 1.000 inches. Then you measure 12 and 6, and let's just say you get 1.500. The difference between 1.000 and 1.5000 is 500. So you'd have a lift of 0.500. That'd be a half-inch lift, something like that. Cool. So that's how we're measuring. But also, it starts to ramp up right around here, I would say. We would need to put this on the V blocks and get a dial indicator on there and measure the amount of degrees. We have to put a degree wheel on the camshaft and measure how many degrees it's from when it starts to ramp to when it ends ramping. Cool. We don't really do that measurement though. Again, I have to stress that. When you buy a cam, it says the duration. So if the duration is 165, you're like, what the heck does that mean? Well, that means for 165 degrees, it's ramping. It's up, it's off of the base circle. There's 360 degrees in there. So that means a little under half is actually ramping. Cool. So continuing. And this looks at duration, but it's more specific. It's called valve overlap. So you would look at what the intake valve is doing and what the exhaust valve is doing. And right at top would be the top dead center. Right at bottom would be the bottom dead center. You may actually find the intake valves overlapping the exhaust valves, meaning if we start with this intake valve right here, the intake valve opens a little before TDC. It opens, it stays opens, it stays opens, it stays opens, it stays. It's past BDC and it's still open. And then it closes. Before BDC, the exhaust valve has already opened right here. So the exhaust valve opened before BDC, which means, look, the exhaust valve and the intake valve are open right there. So if we were to measure right from when they both begin, when there's two of them open, we measure that. all the way through to when there's no longer two of them open, the amount of overlap we have right here would be valve overlap. So it's just, that's all it is. It's the overlap is just how long they both open. And you can look at it in this diagram and it hopefully helps you to visualize it. But the whole reason that we have valve overlap is really that thing we were talking about, scavenging. So we talked a little bit yesterday, Monday, about, let's just say we're on the intake stroke. The intake is in the piston's coming down. The intake valve is open. It pulls air in. We're trying to pull as much air in as we can, right? Compression stroke starts. We close them up, depending on exactly when. Compress it. Boom. Power stroke hits. Exhaust stroke starts. We open the exhaust valve. Then what's interesting, on the top dead center of the exhaust is being like pushed out. But what's interesting is if we were to open the intake valve a little early, the exhaust valve being pushed out will actually generate a force, almost a vacuum, to help suck in as much intake air as possible. That's the scavenging effect. That's one of the reasons that we have the valve overlap. Some of the other things to consider is, it's a little advanced, but I just want to plant a seed right now. One of the problems with our engines is they make NOx, oxides of nitrogen. They make several different emissions, but NOx can be particularly difficult to deal with. We have a catalytic converter that's a little more efficient at hydrocarbons and stuff, but and it can clean up NOx. But one of the ways that we can clean up NOx really well is called exhaust gas recirculation. So we'll slam an EGR on there and we'll basically take the exhaust gas and recirculate it, EGR, back into the intake. And that exhaust gas will displace new intake air, new fresh air, which means the oxygen's already spent, it's inert, it's non-combustible. But what's interesting is because the exhaust gas that's been recirculated is inert and it's non-combustible, that means it doesn't burn. That actually cools the cylinder. So that reduces NOx. That's the whole purpose of EGR, and it's been around since like the 70s. They found out, hey, wait a minute, why are we recirculating the exhaust through the EGR system when if we have a very fast acting variable valve timing, we could actually just let the exhaust valve bleed exhaust back into the intake. And now we've diluted the intake charge fresh air with exhaust air. And we don't even need an EGR valve and an EGR cooler and the ECM doesn't need to control it and stuff like that. So using this valve overlap, we could do more than just make cool scavenging happen. We can actually make the engine burn cleaner and decrease our emissions. So, okay, we'll come back on that a little bit later. Now, let's talk about VTEC. All right, VTEC is the best, right? VTEC, when VTEC cracks, well, let me help you. Here you look at these lobes. These lobes are pretty cool, but this big one right here is a lot taller, which means it's going to have a lot more lift. So these are going to move fairly low amount of air. The big one is going to move more air. Which one do we want? Well, cruising around town, we might want the smaller lobes, right? Those are a little better for mid-range, a little more torquey, going to be a little better with fuel. But like on a VTEC, that's Honda stuff. When VTEC hits, you get a big boost in power. One of the reasons you get the big boost in power is because VTEC will actually change over from the smaller lobes to the big lobe. You guys have a video discussion that actually shows it in 3D. That's going to help make a little bit more sense, but they use a little pin and all three of the rockers go independently, but this middle rocker is just kind of going up and down. It doesn't really actuate the valve. The VTEC engages, it uses oil pressure to pop a pin in. And then the big boy right there is going to be pinned to the actual smaller rocker arms. And those smaller rocker arms are the one that open the valves. It's a pretty interesting system. So this is just pointing out everything you learned about cams is applicable, except VTEC has an extra cam lobe that's much more aggressive, but we only use it when we're under heavy load above a certain amount of RPM. Cool. So there's VTEC for you. Now let's talk about the different type of valve train components. Overall, though, valve trains responsible for moving air and fuel through the engine must be open and closed at precise times. Newer engines are computer controlled and can adjust valve timing, like we're talking about VVT. Fast, especially the faster VVT systems. The valve train incorporates all the parts between the cam and the valve. So this can be drastically different from one engine to the next. So that's why I want to get an overall understanding. And additionally, pop in there balance shafts. The reason balance shafts are here, because a lot of times the balance shaft goes along with the timing belt or chain. So the balance shaft can be kind of lumped in. Sometimes the balance shaft is bottom end. Sometimes the balance shaft isn't really bottom end, but it's driven by the cam or chain. So it's something at least to keep in mind here when we start getting into timing. All right, now lifters. The most common, I would say, currently used hydraulic valve lifters. So it's like a plunger. It's inside of a hollow cylinder. We got a couple pictures coming up, but the oil fills the body. So that means the oil keeps the valve lash to a minimum. Lash meaning clearance, right? So if I were to make this my valve or really anything, this amount of clearance right here, that would be lash. This would be no lash because they're touching, right? So depending on if there's movement or not, like right here, see that? There's lash there. How much? That's a lot. That's like a ½ inch. The lifter, if there's lash, the lifter gets pumped up, the oil pressurizes and it goes poop, the lash is gone. Lifters are cool. They make the lash zero all the time because it uses the pressurized oil from the oil pump to pump them up, and then you're good. So like yesterday we were doing a valve adjustment in class on a Honda. The Honda doesn't have hydraulic valve lash adjusters. It's just got the next slide, which is more of like a solid. We need to fine tune that adjustment 30,000 miles or so, not on the hydraulic valve lifters. So, but this is the negative. It's got the cylinder and a plunger, which means the plunger needs to be kind of sealed to the cylinder. If they're no longer sealed, the oil will just kind of bleed out, and then you'll get a lifter that's collapsed, and they tend to go tick, 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 tick. So lifters are amazing because they lower your maintenance, but if you have a problem with the lifter, it kind of sucks because now you got a tick. And if it got really bad, which I've seen a couple times, it's pretty rare, those lifters could deflate, basically not be pumped up. They can get so soft. The valve train will have so much lash in it. There will be so much lash. It won't open the valve all the way. A completely collapsed lifter could actually cause a misfire because it won't open the valve all the way. Not real common, but it can happen. And so pretty common. Now the next one, solid lifters. It's just, there's no plunger, there's no oil pressure, there's none of that. They basically look like a lifter, except it's just a metal slug in there. There's no complex movement. There's no plunger. There's no oil feed to pump it up. We oil them to lubricate them, yes. Now, they literally just transfer the action of the cam into, let's say, a push rod in this example. That's it. So how do we perform the adjustments? Manually. Just saying. They require valve adjustments. They can also be noisy because if you think about it, right? On the lifter, the lash becomes nothing. But in this system, because there's no way to have the oil, right? The oil pumps it up, but the oil's not strong enough to hold a valve open. So it's like we can run zero lash in a hydraulic lash adjuster, but with a non-hydraulic, with just a solid, we need to leave some space there. Because as that valve expands with heat, we need to leave it some room to expand. So we may be running 7/1000 of an inch on the intake and 11/1000 on the exhaust. Well, that's lash. So if you try to clap your hands like this and they're already touching, you didn't make any noise. But the more space they have, the more lash they have, the more clap you get. So that's what they mean by they're typically a little more noisy. It's just the way it is. If they're adjusted right, they're not excessively noisy, they're normal, but they are more noisy than a well-functioning hydraulic lifter system. Cool. But they could be lighter. So, if you're talking about Honda S2000 that runs 8,000 RPMs, yeah, they're a little better for running higher RPMs because they're not going to valve float, right? Because it's just less moving material. There's less mass spinning. It's going to stay a little tighter. Cool. So here's another example. This would be a solid type. This doesn't have any plunger or anything like that. This is, I actually, a lot of times we'll call this a bucket. So the reason I call it a bucket, if you look like it, if you were to turn this over, it literally looks like a bucket. So sometimes they'll call this actually a shim under bucket. This little red part is indicated to be the shim. So if this bucket rides on the camshaft and this is your valve that's completely seated, there needs to be a specified amount of measurement right here between the valve and the bucket, which maybe we'll call like a follower, right? It's technically a lash adjuster, but a lot of times we would just call it like a follower or a bucket. So there needs to be a certain amount of clearance there. Now, over time, remember, the valve is opening and that's not that hard. But when the valve is slamming closed because of that valve spring, this valve right here has the seat. And the valve seat is getting smacked in the face, just punched all day long. Bam, 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 bam. Eventually, especially if you're running higher RPMs and stuff, the valve is going to beat its way into the seat, which means the valve is moving upward with wear. As the valve moves upward, this clearance of 7,000s becomes 6 and 5, then 4, then 3, then 2, then 1, then 0 is no clearance, and then ultimately 0 becomes negative, which means the cam's not moving, right? The cam's like, I'm got all my cam bearing saddles and the journals and the caps, all this. It's not moving. But basically what's going to happen is the bucket is going to stay still. The valve is going to be trying to push its way up. And instead, it's just going to hold it down. It's going to hold it open. Because now to seat, the cam needs to go up higher to reach the seat. But the cam can't go up higher to reach the seat because we have no more clearance and it's running into the bucket and it won't move. So we hold the valve open. Remember, that's what we talked about. That's how you burn a valve. That happens. That is the main reason we do valve adjustments. It's not because the cam, lobe, base circle is worn. It could be, but that doesn't really happen. So it's really because it's beat its way into the valve seat and this got tighter and tighter and tighter. Now what we would need to do is pull the cam off, pull the bucket off, and put a thinner shim in there. So if you had a 50,000 shim and you were down at 0,000s and you needed it back to 7, you'd probably put in like a 43,000 shim, right? If you put in a 43,000 shim, now there should be 7,000 clearance again, right? We could go nuts on the math. I've even seen a lot of technicians get kind of confused on what size shim and whatever. It's really, I don't look at the formula. There's even a website where you can put your current valve clearance and what your valve clearance you want and your shim size, and it'll spit out a number. I just find it so simple. If you want 7,000s and you only have 2, you want 5 more. Then you just got to think about, you want a thicker shim or a thinner shim. If you look at this little red shim, if you were to put a thicker shim in there, that's only going to tighten the valve up and hold the valve open more. So if you want more clearance between the bucket and the valve, you need less of a shim. Think of it maybe like a sandwich, perhaps. If you had a lower piece of bread, that's the valve, and you had an upper piece of bread, and that's the cam, and in between the two, you wanted 7,000s. You have 7,000s for your meat. That kind of sucks, by the way. That's a thin sandwich, but you have 7,000s for your meat. Oh, but all of a sudden, you, let's say, have only 2,000s for the meat's probably not really a good example. Let's make it just air because you're on a diet. You can't really have you can't even have the meat. If you are supposed to have 7 thousandths clearance, but instead your sandwiches are too close, you would actually need to get kind of like thinner pieces of bread, right? Your pieces of bread are kind of too fat. You need less. You need less bread to make more air gap. You want a 7 thousandths air gap and you don't have it, you basically need to get little thinner pieces of bread. It's kind of the way that I would think about it. We could think about it in a whole bunch of different ways. But if you put a thicker shim in there, the thicker shim means you're like thick pieces of bread. You don't have any space anymore. Cool. So that's pretty much what we're doing. We're changing the thickness of the shim. Cool. How much? Depends on how much you want. You got 2 thousandths of an inch, but you're supposed to have 7. Sounds like you need to get 5 thousandths thinner pieces of bread. And then you'll be back to having your air gap, your clearance of 7. Cool. So pretty good. Now we'll continue. This is a different style. Camshaft is spinning, but as you notice, it's not pushing on a bucket, right? This is basic. This is 2JZ style. That's how that is. This style, camshaft is spinning, but it's pushing on a rocker arm. The rocker arm is going to ultimately push the valve down. However, the rocker arm also bridges over to this lifter, and that's actually a hydraulic valve adjuster. So this lifter has a hole in it. That's going to get the oil pressure. When it gets the oil pressure, it's just going to pump up. So let's just say, as this valve gets the valve seat recession, which means the valve beats its way up into the head, as the valve beats its way up into the head, it's getting closer to the cam, but no problem, because what'll happen is it'll just push up a little bit, which will just push the rocker down a little bit, and the oil pressure's not so strong where it can possibly hold the valve open. See, so we don't have to worry about a shim. Now, yeah, they do have a little spacer right here, but the purpose of that spacer is really just to not wear out the tip of the valve. That spacer is like just like a little cap, basically. And the cap is going to touch the valve and the cap is going to touch the rocker. So if anything, that little cap will get worn out over 200,000 miles. Then you don't have to get valves. You just have to put caps in. So it's a way to save money on a rebuild. And also, they might harden those. There might be another little bit of a reason too. And so if you just think about that, this lifter is going to constantly be pumped up and constantly provide the exact lash adjustment that you need. It's going to basically maintain 0 lash. Valve beats up into the seat, no problem. Lifter just backs off a little bit. Something crazy happens, like you take this valve out and you machine some of the tip of the valve off. No problem. Lifter's like, well, I'll just pump up a little bit more. The lifter has a lot of travel it can take up for all that. This style is actually pretty common. Like on, for example, a lot of the dual overhead cams. So this is on a 2GR. In fact, this is on the A25A2. So it's typical. It's low maintenance. It makes a lot of sense. Now, other would be, this is that bucket style. So the bucket we saw a cutaway of here. But this is what the bucket actually looks like. Now, commonly, the buckets would have a shim. That's an effective way to do it. Sometimes the shim is on top. Like this one's a little bit hard to see, but it seemed like there could be a shim on top, which means the shim would actually come off the top. So on those, the valve adjustment's kind of nicer because you could loosen up the cam just enough to take the tension off the bucket. And then you could use a magnet and pop this whole little cap off. And that is the shim. And if you can slide a thinner shim in, you can do the valve adjustment like that. But if it's like this, that shim is under the bucket. You got to pull the bucket all the way off. That means your cam is out. And if your cam is out, that means your timing chains are off. That means your timing cover's off. Some engines actually, and it's not real common, but some engines actually make it where there's holders and you can hold all your sprockets, and you can basically slide the sprocket out a little bit, and then you can remove the cam without pulling the timing cover, without pulling the chain. That's pretty cool, but that's not real common, right? So if it's more typical, this valve adjustment's going to suck. You can get paid more, but it's going to be a lot more work. If it's a shim over bucket, you might be able to sneak those. There's another type though. So shim under the bucket, shim over the bucket, or it's one more type. No shim at all. They're called selectable buckets or sizable buckets. Each one of these buckets has a specific thickness, and a lot of times they have a little number on them. So if you needed a thinner bucket because of that valve seat recession where the valve beats into it, you would actually have to take the bucket out, measure the bucket, and let's say the bucket's 300 thousandths and you want more valve clearance, maybe you need a 295 thousandths bucket. You'd have to actually replace the bucket with the right bucket. And parts department isn't going to want to stock a bajillion buckets. So here's what they're really going to do. They're going to be like, oh, if you need to go through one of those heads, we send that out to the machine shop. Now I'm going to back up, click, click. This is what the machine shop can do. ASE concept also, by the way. If you needed a thinner bucket, the machine shop says, nah, we can make it work. You need a thinner bucket by 5 thousandths of an inch? I don't think so. We'll take the valve out, we'll put it on our machine, and we'll grind the tip of the valve 5 thousandths shorter. Put it back together. Now all of a sudden, boom, you got your 7 thousandths clearance or whatever the number is. Make sense? So a good machine shop doesn't need to stock a bajillion buckets. A good machine shop can actually grind the tip of the valve to restore the valve clearance. So you send that head out to the machine shop, they'd be able to tip all those valves and get all your valve adjustments in spec without buying any buckets. If it's an adjustable, like a Honda with the nut and the lock nut and the screw, that you don't need to machine it. If it's got hydraulic lash adjusters, you probably don't really need to worry about valve adjustment because the lash adjuster, the lifter, is going to take care of it. But if it's like solid, it might actually be a lot cheaper to send it to a machine shop that can machine it than to buy a bajillion grips of buckets and shims and stuff. Okay. Other thing is, let's just say that you have 20 thousandths of clearance here and you only wanted 7. Well, that means you got to tighten this up by about 13. How are you going to tighten it up? To tighten up a gap, right? If there's a gap right here, you slide your feeler gauge in and you got a gap of 20, but you want a gap of 7. That means you'd have to lift this bucket up by 13 thousandths. You can't weld on the valve and add 13 thousandths. What you could do, however, what the machine shop could do, I should say, you could take the valve out and you could cut the seat 13 thousandths deeper, and that'll actually move the valve up 13 thousandths, and then all of a sudden you're back to your 7 number. So a good machine shop can actually fix both a loose fit or a tight fit. We may call that, if we're talking about clearance, here's your sandwiches again, here's your bread. If you're supposed to have 7 thousandths of clearance, but you have 2, that's insufficient clearance. That means it's too tight. There's insufficient amount of air gap there. Insufficient valve lash means too tight. That means you need to make more gap, which means probably you need to thin your bread. You need to get thinner pieces of bread, which means you need a smaller shim. If you have excessive air gap, that means like, hey, between my pieces of bread, there's like 20 thousandths of air right there. I only want 7. That means you need thicker pieces of bread. This would be excessive clearance. There's too much clearance. There's too much air between the two. Excessive valve clearance or insufficient. You need to know those words. If you're confused, you ain't getting the question right. You'd be like, insufficient. I understand it, but you got to draw me a picture. Well, you ain't getting a picture. I'm giving you the picture. Insufficient clearance means there's not enough gap. Excessive clearance means there's too much gap. Fair? Because we're talking about the clearance. If you were going to talk about your sandwich, if you say, I have insufficient sandwich, that means you want bigger sandwich. If you have excessive sandwich, that means you can't finish it. You need a smaller sandwich, right? So when we talk about clearance, we're specifically looking at it from the perspective of the gap of air. Okay, kind of makes sense, hopefully. Cool, so we could do a lot of that type of stuff. By the way, they would call this grind the tip of the valve, and right here they may call seat grind, or sometimes they call it butt grind. Got some different terms. ASE would probably just say grind the seat, cut the seat.
Is that also where like valve lapping comes in, like what you were talking about yesterday?
A little different, but actually we're gonna cover valves a little bit more. So lapping the valve is more, best way I can explain it, it's like a relationship. So if you're in a relationship with someone, you know, they might have little imperfections and you might have little imperfections, but you got to kind of wear together. So it's gonna be like, hey, um, when you um when you do this, it kind of bothers me. So can you like kind of chill that down a little bit? It's sort of like if a valve has a big bump on it and the seat's like, man, that bump kind of hurts me. You need to grind the bump down, right? So that they can be well fit. So when we're putting that lapping compound on, it's gritty. It's like liquid sandpaper. Boom. And we're putting it in the seat and then we're spinning the valve. We're basically using that compound to kind of lap them in. And now all of a sudden it's like, hey, you know what? You used to have a bump, you used to have this thing that bothers me, but I don't really feel it anymore, you know, because the lapping compound wore it down. And now those are perfectly meshed, perfectly fit pair. Now, if you yank the valve out of there and you put in a different one, you put a new valve in there, it's like, oh, here we go. This valve was machined by a different tool, and I don't really like the way it fits up against, you know, my valve seat or something, right? So we're essentially marrying the two. We're just marrying them, which just means they're going to fit together perfectly. It's not, it doesn't take any substantial material off. It doesn't really change the clearance. However, if we were to go to that big blue machine and actually cut new seats into it, that's not gonna take a little material off. You're like cutting a whole new seat, like, or grinding it with the stones. That's actually gonna move the valve closer to the cam. Yeah, so lapping, no, but actually cutting new seats, yes.
Gotcha.
Lapping will occur in the dealer. Cutting new seats is not gonna happen in the dealer. The machine shop's doing that.
All right, cool. That makes sense. Thank you.
No problem. Good question. Here's another example of like a flat tappet. So this looks like a lifter, except there's no roller, there's no plunger. It's literally just a slug of steel. No moving parts. Old school. Needs a lot of regular maintenance, more adjustments and whatnot. This is the one I was kind of telling you about though. This slides right across the cam, and there's a lot of friction right there. And this is why back in the day, those oils would have zinc and stuff in them. The oil, and that's also part of the reason to be like, you need to change your oil all the time. Like if you had an old cool hot rod muscle car and it still had this design in there, you're not going in and buying the same oil as your 2024 Camry. It's going to be a different oil and it's going to have different additives in there because you have a lot of friction right here. You got 8 cylinders with 2 valves per cylinder. So you got 16. You got 16 of these flat tappets sliding across there. You need an oil that's made for that. Cool. So I don't know. I don't think that was really a very good design, but at the time, hey, it worked. It was all right. Now, here's your flat tappet. Here's your flat tappet type lifter. So this slides across the surface. This is the same piece. It's just upside down. Okay. This slides across the surface. So now you're talking about needing the zinc and stuff, but it's got a plunger built in. And this is one of the better pictures I've got of this plunger is going to accept that push rod and it's going to basically take oil in this hole and it's going to pump it up and it's going to keep zero lash on the push rod, zero lash in the valve train. Roberto, go ahead.
So I'm kind of confused on what that flat tap does.
Okay.
I'm trying to
Look right
understand what
here.
you're saying.
It's on it's on the lobe, right? You see how it's sitting on the lobe? Well, when
Uh-huh.
it turns, think of when it gets to the lobe and the lobe is pointed, right? If it's sitting on the lobe and the lobe starts to ramp up, what's it doing to the tappet?
Pushing it.
Exactly. And the tappet is going to accept the push rod right here. Like you can actually see this is no longer the tappet. This is a push rod right there. So if the lobe pushes the tappet up and the tappet pushes the push rod up, the push rod pushes the rocker arm up and the rocker pivots and pushes the valve open going down. So
So
they just
over
ride. They
time,
just basically ride on the cam. They just ride around and they go up and down because they're being ramped. Kind of makes sense?
yeah, can it work like over time since it's just lapping it?
Exactly. And so that's like, it's just lapping around and around and around and around. And yes, it can. That's part of the reason I was saying they really need the correct type of oil. The zinc is supposed to minimize or prevent that wear. And so you got an old car like this, you can't just be putting your basic oil in there. That needs to be like high zinc treatment. I used to actually have some old oil that was like that, but I don't anymore. So you'd see an oil that would be like high zinc or whatever, would be more for that. This one would need it too, because it's old school. This is still sliding across it, but can you see the difference? This is a Tappet running laps around the cam, but on the other side where the push rod goes, it doesn't just go to a basic slug piece of steel. It's got a plunger. It sits in this plunger. It tries to push this plunger down, but the oil pump pumps it up and sends oil into this, which has a little seal, and it pumps the lifter up. And then that takes out all the lash. It makes it so that like you don't have to do any valve adjustments. As the stuff wears, the lifter will just plunge or not plunge or pump up more or pump up less, totally eliminating the lash. Lash being the space, right? Lash is the clearance. Oil, valve clearance and valve lash are the same term. Sometimes I switch them interchangeably. I want to switch them interchangeably because I want you to know both, but don't let it trip you up. Valve clearance, valve lash, both talking about the little air gap, the little space. All right, cool. So that one's good. This doesn't require the maintenance because it's got the hydraulic lifter built in that pumps up. And now this is much more up to date. So we've got the lifter part that pumps up, but down here, we're not having a flat tappet that's sliding across the cam. This is a roller. So with a roller, this is going to spin. It's got a little bearing in here. So this is just going to spin. So that's not going to slide across the camshaft, which means it's not going to make as much wear, which also means it's going to have less friction probably. So some people were putting roller lifters in to have it make more power. And you're like, how does that make more power? Well, if it reduces friction, technically it's freeing up some of your power for turning the transmission rather than sliding the tappet across the cam. So roller lifters are good. Roller lifters have become normal starting like, shoot, I don't know, in the 90s. So if you've got older than that, maybe not. But if it's like 90s, 2000 and newer, you're not going to be seeing a lot of flat tappet stuff realistically. You might see a mix in the 90s, but much after that, you're not going to see a whole lot. All right, so that's got kind of the best of both worlds. And then lash adjusters that are more like manual, as you can see. We've got a lock nut right here and a screw. So this is how we would adjust the lash if it was a manual adjustment, let's say like the Honda. If you look right here, this is the rocker arm. The rocker arm pushes down on the valve. The cam sits in this saddle right there. So that's where your cam journal is. That's the round one. But then your lobe is going to actually push on this rocker. So we were talking about, Nate asked a good question. If that cam lobe is worn, are we machining? Well, the cam lobe is putting out all its wear right here on the rocker. A cam lobe wouldn't wear this. A cam journal would wear this. Then we're potentially machining and replacing a head. But if it's a lobe, yeah, it messed the rocker up. That means we take the rocker out. We get a new rocker. We get a new cam, and then we're good to go. However, like on that Polaris I have, that thing was so worn, it was nuts. There was a lot of metal throughout my system. So this would wear a little bit, and then the metal would get in the oil, and then the oil would drain in the pan. Like part of what helped me figure it out is I did an oil change, and it was kind of silvery. Like it wasn't, there was a way more metal than I've ever seen. And I'm like, oh, okay. Yeah, I got something wearing in there. And the fact that I'm losing power and wearing, I don't think it's the crankshaft. The crankshaft doesn't make you lose power, but a cam could. There was a lot of, how to say, mucho pienso. I have those long motorcycle rides in and back, and I'm thinking about stuff the whole time. By the time I get there, I'm like, already thought about 10 different things, but I kind of thought about it and it made sense. So that's why I took the head apart, popped the cam out, and like, oh, this is worn. The rocker's worn. It was all kind of, they had worn each other out, That's kind of the problem with being a matched pair. If there's a problem with one of the parts and it's rubbing up against the other part, you got two parts that have a problem now. I could bet you right now. Cool. So continuing, rocker arms is one of the next thing we cover. There's a lot of different types. It depends. Is it going to be overhead valve, overhead cam? You know, there's just a lot of different designs. So let's just jump right in there. Also a term for you. The ratio has to do with the pivot point and how much it moves it. So if you just looked at like a teeter-totter, you know, the seesaw, the things you'd have in the playground, if the pivot point's right in the center, well, let me see if I can make it right in the center. The pivot point's right in the center. Whatever you do on one side, it's going to affect the other side equally. But if I were to move it here, now if I were to move this side a little bit, it would move this side a lot. So you can actually make it so that the rocker arm could move the valve more or less depending on the ratio. So let's just say you wanted more lift, you could actually get a rocker arm that would take your existing cam, but it would throw the valve further because it would move the pivot point. So that's what they mean by ratio. Now for ASE, never going to talk about ratio. For building race car stuff, they might talk about ratio. Okay. Now let's continue. So here's some rocker arms that are mounted on a shaft, and they could still potentially do this. I've seen a few things that are newer, but this used to be more common back in the day. If you look, this is your rocker arm right here, and your rocker arm goes between a push rod and the valve, but it has to be, the pivot point has to be something. And in this case, the rocker arm is mounted on this long shaft right here. All the rocker arms are sitting on that shaft. And I told you guys about something I was picking on, you know, DIY rebuilds that are done in the garage, and they don't really have a way to clean it. But I told you I had a neighbor and his push rod popped off. And after some extensive diagnosis, we figured out, hey, your rocker arm is not moving real freely on the shaft. So we had to pull the shaft apart, pull all the rocker arms off, find out that what happened was there was actually rust inside the shaft, and they send oil into that shaft. And then there's a hole at each one of these rockers, and actually the oil was pushing the rust into the pivot point of the rocker arm. And so the rebuild was crappy because they just didn't really have a way to get all the rust out and clean it. Like they don't have a sonic cleaner. They didn't have a media blaster. They had their garage and they were using like a rag and brake clean apparently. So if your rocker arm is pivoting on this shaft, then you know that's kind of its design. It's a shaft mounted rocker arm. Now there's a lot of other ones. Pedestal mounted's different. See, so these aren't all on a long shaft. They have their own little shaft, and they're mounted on a pedestal, which is kind of like a stand. So there's a bolt that goes right through here, and the bolt goes down into the head, and it's mounted on the pedestal, and then it rotates on its own pedestal. Now, sometimes they'll call this a trunnion, and like the LS, for example, you know, they're pretty good, but like if you're starting to try to do really high RPMs and big power, these trunnions, because it's pedestal mounted, actually had some issues. So they have like big trunnion upgrades and different high performance type of things. If you're going to be really going very aggressive on your cam, because the more aggressive your cam is, the more this shaft, this rocker arm is going to have to move a lot of up and down, you know, so they might beef up this little bearing. You can see that bearing's in there. So the pedestal mounted is another, it's a good one. Like it makes sense. It also allows for precise alignment no matter where the valves are located. So like some of those other ones, you know, on that shaft mounted, you know, they did pretty good, but you were limited to where you could mount the rocker arm because it's all on the shaft. Or if it's a pedestal, they can mount them anywhere, and they'll design all that on CAD and be pretty nice. Now, a couple types, some rocker arms are adjustable, but that's like not real common. That'd be like that Honda one, right? So let me jump back. This is adjustable. You're looking at the rocker arm, and there's the adjustment. You know it's adjustable because it takes a flathead screwdriver right there. You won't be able to turn it until you loosen up the nut, but that'd be adjustable. Most of them though, not really gonna be adjustable. They don't need to be adjustable because they use a hydraulic lash adjuster, and the hydraulic lash adjuster, AKA the lifter, is going to make up the wear. So we don't need an adjustment. You're done. You just put the rocker arm in or you take the rocker arm out. They also have some other ones that are like rollers. So roller rockers can be factory, but this example is like high performance from Jigs. Get in the zone, auto zone, or whatever. So this is a high performance one. This is pedestal mounted. This may actually have a roller. You know, sometimes they have some pretty cool fancy upgrades on those. But other times they're from the factory. They're just rollers from the factory. Like Toyota uses a lot of roller rockers. If you look at it, the roller is actually on the center of the rocker, and that's what rides on the cam. So it's, you know, it's good. All right, so pretty simple. And then this does talk about the performance rockers. They'll move the fulcrum, the pivot point, and that could potentially increase the amount of lift, increase the valve, the amount that the valve's open. Now, when we're doing camshaft work, remember we talked a little bit about how to measure it. So this is going to get more into like some of the measurements we're actually going to do, not the theoretical JEGS parts. If we wanted to do an overhaul, we would need to know if we have good oil clearance on all those journals like we were talking about before. So this one has 1, 2, 3, 4, 5 journals for 2 cams. So you have 10 total journals. You need to make sure they have the right oil clearance. You could do the math, like we said. You could measure the cam journal, and then you could measure the bearing, or it's not really a bearing. There's no bearings on this aluminum head. You could put the cap on and you could measure the saddle. So the diameter of the hole, you could measure that. And then you could measure the diameter of the cam and do the math, right? And if you've got 2/1000 clearance, you're good to go. Or you could use plastic gauge. Plastic gauge we mentioned once, but you could take plastic gauge, which has this little strip of plastic, and then you'd lay a little strip of plastic in each one of these, right? So that just got a strip laid in there. And then you'd put the cap on, you torque the cap to spec. Do not spin it, because then you're just smearing your pancake all over the place. You don't want to smear it. Okay, so you just literally put it on, tighten the cap down, and if the oil clearance is less, it'll get squeezed tighter and tighter and tighter, and it'll make the puddle, it'll make your pancake mushed out. Okay, and if it makes it mushed out, then you know, hey, I don't have a lot of oil clearance. Or if, let's say, you have not a lot of oil clearance, there's a big space there, right? You have excessive oil clearance, which means your cam here and your cap only comes down to here. It might barely disturb that plastic, and your plastic would stay really thin. That would mean you have a lot of oil clearance. And how do you measure it? Well, you've got all this, this whole strip right here has a way to measure here, a way to measure here. You'd actually normally rip it. And if you rip it and then you look right here, this one, for example, the schmear right there goes along with the 0.038. Now this is millimeters. So let's say that's about 1.5 thousandths. You'd be like, okay, I have 1.5 thousandths. If your range is 1 to 2 thousandths, that would be good. And you'd move on and do it again, 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 and again. This would do a journal. 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 But inside this paper, there's that long, looks like dental floss style plastic. So you'd have to, what I normally do, cut this one, cut this one, cut this one, cut this one, use the plastic for a journal, use the plastic for a journal. And then essentially you're just using the paper for a gauge to measure. All right, so that's pretty much how the plastic gauge works. Cool. Now we also need to measure thrust, which you could also consider end play. This cam can move back and forth. But to measure that, we wouldn't really use a feeler gauge. Some people would try. What we'd actually do is rig up the snake and the dial indicator, put it on the end, and then actually try to move the shaft back and forth. That's just a thrust measurement. That's it, camshaft thrust. The The crankshaft, we're going to measure that too, but that's for unit 3. So for this one, these don't have thrust bearings. You know, a lot of times they'll have a plate, or they might just have the way that the cam is made and sits in the head and the saddles. They shouldn't really have a whole lot of movement. And that's how you measure it. Measure the intake, measure the exhaust. If it's in spec, we're good. If it's not in spec, well, then you have to figure out what controls the movement. A lot of times TIS, if you're following, it's going to say, if this measurement's excessive, replace the cam. Or if it's a crankshaft, they're going to say replace the thrust bearing. Cool. Another one, like let's say we're going to disassemble the head, which you guys got to get a little bit of a preview on. You're going to put it in the spring compressor, which is going to push down on the spring, which is basically just relieving the tension so that you can go in with your magnet and grab those little keepers. So we grab those keepers right there. We take those keepers out, and then we'll release the tension. And then that whole spring will be able to be taken out. And that means we can take the valve out. Now we need to take the valve out because we need to do a lot of measurements on our valve. So for example, you're going to measure the valve for overall length. That's an important one. What tool are you going to use? Well, you can use a couple different ones. Maybe you use a dial caliper, a digital caliper. You might even be able to use a stainless steel rule, but I'd say that might be a little tough because then you're going to be like trying to eye it up and, you know, trying to make sure that you're seeing the right line lined up. So when we're doing precision measurement, we want to use the method that's going to be the most accurate, right? So valve stem diameter, we're no longer using the caliper, we're using the micrometer. So we're going to measure in multiple places, right? So let's just say top, middle, bottom. But also, if this is 3 to 9, we also need to measure 12 to 6, right? Now, if we have a difference between 3 and 9 and 12 and 6, what's that tell us about the valve stem? What's that tell us about the valve stem? That's out of round. Exactly. So if we have a difference between top and middle, the top is, let's say, 3 mil, we'll make it 1,000. The top is 300 thousandths, and the middle is 295 thousandths. What's that tell us? That's not out of round anymore. That would be tapered. So tapered's a different type of wear. They'll give you measurements like if your minimum right here is 300 and you're at 299, that valve needs to be replaced. But if that valve's been going up and down, right? Like a lot of this has to do with, it's just so hard to not make it about people because people are so much more understandable. These are partners. These partners have worn together. So if this valve has gone up and down and this valve is worn, the partner wore the valve out. So the partner is going to have wear as well. The partner would be the valve guide. So this, Toyota likes to call it valve guide bush, but the valve stem has slid up and down in the valve guide or the valve guide bushing. So if you're seeing an issue here, you definitely need to be looking down here. Even if you're not seeing an issue here, you still need to be looking down here. So we would go ahead and we'd measure that valve guide. And let's say that we could use an inside micrometer, but a lot of times we're going to use that small hole gauge, something I demoed a little bit in person. You'd go ahead and use the small hole gauge and do a measurement. If your valve guide is different between 3 and 9 and 12 and 6, that's also at around, right? If your valve guide has a small measurement at the top and a big measurement at the bottom, that's also taper. So there is some repetitive stuff, like that's just the way that it is, taper and out around, taper and out around. You're measuring taper and out around on a whole bunch of different things. Cool. Now, I know I went a little bit out of order from what you thought, but the valve stem and the valve guide have, they go together. Make sense? So continuing, oh, let me give you a little bit more. We talked a little bit about this, but if you had a valve guide that was worn or a valve stem that was worn, they'd have excessive clearance, right? So how do you measure the clearance? You can't plastic gauge these. There's no way to plastic gauge this. What you do, you measure, let's start with the valve guide. You measure the valve guide, and let's just say we'll make the valve guide, I'm going to make it really easy math. The valve guide is 10 millimeters. Then you go to measure the valve stem, and the valve stem is 9 millimeters. What's the clearance? That'd be 1 millimeter. Exactly. Perfect. Now, 1 millimeter, good or bad? I don't know. In reality, that'd be bad, by the way. But then you'd go and look at the specs and you'd be like, oh, what's the maximum clearance? And if it were to say the maximum clearance is a 0.5 millimeter, you're like, oh, crap. I'm only supposed to have a 0.5 millimeter. I have a whole millimeter. Well, that's a problem, right? But like I explained, you need to not only identify that's a problem, you need to know what would that problem cause? And what would you do about that problem? How would you fix it, in other words? So first things first, here's your valve guide. Your valve guide is right here, right there. And here's your valve stem. And they're sloppy because you have 10 millimeters and 9 millimeters, and there's too much clearance. What do you think that's going to cause for the customer? What's the customer's concern?
Noise?
It wouldn't cause noise. Good guess. What we got to worry about is, remember, there's a valve guide seal right there. And the valve guide seal is going to be fitting pretty tight to the valve stem because remember, there's oil sloshing around under the valve cover. So if there's all this oil sloshing around and the valve seal isn't sealing well to the stem, oil's going to get on the stem, oil's going to run down the stem, and oil's going to drip into your cylinder slowly, especially as it sits overnight for a long time. And then you're going to start in the morning, you're going to get a big old puff of smoke. Poof. You're like, what the heck is that? It's oil consumption. It's burning oil, but it's burning oil, especially on morning startup. It's a really good indication of valve guide seals.
What's
But the
wrong with the
point of
smoke
this lesson is so you understand if the valve guide is worn and the valve stem is worn, it's sloppy like this. Valve guide seals aren't going to fix it. You're not going to be able to put valve guide seals in it and be good. There's just, you'd have to tighten that up. How do you tighten it up? Maybe it's mostly wear on the valve stem. You put new valves in, you're good to go. However, it could also need the valve guides to be smaller, which is harder, right? Like to change a valve stem, no big deal. But if you have a guide and it's supposed to be this big, but it's this big, how do you make it back to this big? Generally replace it. You're generally going to have to replace that. And in this case, those valve guides are not something you can replace. Those are integrated. They're integral in the aluminum. They were cast in the aluminum, which means you need a head. There is a couple of exceptions. So like machine shops exist basically to save us money, so you know, and do stuff that we don't really have the expertise to do. But a good machine shop should justify themselves because like, hey, we can do the work that you can't do and we can do it cheaper than it costs to replace it. Because you could always replace stuff. You don't need the machine shop. You can just buy it new. But if the machine shop is good, they'll be like, look, you need a new head, or we can fix those valve guides. They can do a process called knurling. And the way I explain knurling is sort of like, if you guys have ever seen a farm field, right? And the farm field is dead flat, cool. But when they bring the tractor that has kind of the teeth and they sort of like rake it out, you know how it pulls, it makes a little low point, but it also makes a little high point. So it makes those little rows of dirt mounded up. It's like a mound and then a low spot and then a mound. Knurling kind of does that. Knurling will actually pull some of the metal up into a pile. And next thing you know, it's actually tightened your valve up in there because you can knurl it up and then you can ream it to the right size. And now your valve is riding on those little piles. Is it as good as it was from the factory? Probably not. But does it fix it? Yeah. So knurling valve guides is a way to tighten up the valve stem to valve guide clearance that could be excessive. Okay. Now a little bit more stuff. Let's jump back on the valve. Since we're measuring all over the valve and stuff, there's another thing that we have to do, the margin. The valve margin is that little flat measurement you can see right there. That little measurement is basically like your buffer. It's almost like your like margin would be like profit margin. So if the dealer is selling Tundras and they're selling a Tundra at 50, but the dealer buys it for 40, their margin would be $10,000. That'd be a nice fat margin. If you got a fat margin like that, you can afford to make some mistakes. You afford to make some deals. Be like, yeah, I'll give you some deals. Oh, what's that? You want some methods on there? Yeah, if that's what it takes to make the deal. They got a big fat profit margin of 10 grand. By the way, the dealer does not have a profit margin nearly close to that. So, you know, it'd be very easy to run a business on that big of a profit margin. They don't have it. So if your margin's thinner and thinner and thinner, next thing you know, you only have a $2,000 profit margin, you really got to watch it. Or what could happen? You're going to get burned. It's the same with a valve. Your margin is partially what's going to keep that valve from overheating. It's extra metal. It's kind of like a rotor. If your rotor's thin, it's going to have a tendency to burn. If your rotor's thicker, you got, you know, a little bit more ability to handle the heat type of thing. Cool. So here's your margin thickness. The other way you could think about that is like your bank account. If you need a minimum margin balance of $100 and that's your minimum, well, then you can't go below that minimum. If you're looking at $101 in your account, you can't spend any money because you have a minimum of 100, right? Now this has a minimum. When we grind a valve, we're grinding the face and that's going to fix it, right? So like we were talking about partners. So if your valve gets some defect on the face, it's probably going to get a defect on the seat. And that's actually the next page, but you can fix a valve. You can grind a valve and get a nice new face on there, kind of like resurfacing a rotor, but there's a minimum thickness on the rotor. Well, there's a margin on the valve. So that's your minimum balance in your bank. If this margin's $100 and you're at like 101, you know you can't grind that valve. That valve is junk. If your minimum margin is 100, but you have 300, then cool. Like maybe we grind the valve and then recheck it. If we grind the valve and the valve looks perfect and we check it and the margin's still 150, then we're good to go. That valve's not going to burn. Cool. Now, spring length, that's easy. Take the spring out, use your dial caliper. You're going to measure the free length. ASE may call this free length of the spring. Then there's another one, which is deviation, which can also be called spring squareness. But this is a square. It's an actual perfect 90-degree perpendicular angle square. It's a tool. Everybody should have one. Which you probably won't use that much on cars, but you might use it for housework. So if you lay the square down a flat surface and you set the spring up against it, if the spring is nice and square, it should stay against it the whole time. But generally springs aren't that perfect. So we're allowed to have some deviation. Deviation means it's coming off of square. It's not exactly square, and that's fine, but there's a limit. So you'd be sliding a feeler gauge in there. And if it says you're allowed 20 thousandths deviation, and you can slip the 20 in easily, and then you can slip the 30 in easily, that means it's excessive. It's basically arcing to the side, and you're only allowed 20 thousandths gap, and you have more than 20, that spring needs to be replaced. Or if 20 thousandths is the max and you can't fit the 20 thousandths feeler gauge, then you're good. If you really want to know what it's got, you keep trying. And then let's say you get to 10 and it takes the 10, but it won't take the 11. Then you're like, all right, I got 10,000 spring deviation. Well, cool. You're allowed 20. Okay. So if it's 10, you're good. Right. But we don't just look at it and be like, oh, that spring doesn't look good. You know, you're going to perform some actual measurements and inspections. So just rolling right into the next one, valve seats. As the sun is coming to get me, the sun's getting higher. So valve seats are, like we were talking about, those are kind of like partners again. Your valve has a face on the valve, and it has to seat on the seat of the head. And so this is something we showed, but we've wiped Prussian blue on the valve here. inserted the valve into the guide, and then went slap, and then pulled the valve back out, and you're looking like, oh, okay, yeah, that looks pretty good. We're good. But if you were to see a spot where the blue disappeared, that could actually indicate the valve is bent. If you were to see the blue kind of break up, you could actually find the seat could be damaged. If the valve is damaged, basically the seat's damaged. That's partners right there. If the spouse is damaged, the other spouse is damaged. Make sense? So this is gonna basically tell you what needs to be done. If it's really messed up, like it's missing a big old gap, you're like, I don't think that lapping it's gonna fix that. Then you may have to replace the valve or grind the face of the valve and then cut a new seat, or even sometimes you can have the seat replaced. Sometimes it's so bad you have to replace the head, right? But if it's pretty minor, like this one looks really good. It's hard to tell right there. It almost looked like it kind of lightened up right there. That would be a good candidate to just lap. You know, you put the lapping compound, which is that sandpapery stuff right here, slide it down there, spin it, and that's basically gonna lightly sand down any small defects on the face of the valve, which is contacting the seat, the valve seat in the head, and they're gonna sand them together, and then they're gonna be great. Now, as for angles, this is a 3-angle valve. It's got a 30, a 45, and a 60. So as the air comes around the seat, the more angles there are, the more smooth it is for the air to get in there. If you just had 145 and that was it, you'd have kind of like big jagged edges, and those corners can kind of like interrupt the airflow. So that's why you'll a lot of times see multiple valves. If you want a really high performance, you could do like a 5-angle valve job, and that's going to be almost rounded. If you wanted to get into porting, you'd actually keep, you know, some of these valves, but then right here, you see there's a little jagged edge right there. You could actually take that edge, right there and grind that down, and that'll make it more smooth. And that's how you could do some porting work. So if you've heard of ported heads, a lot of times that's what they'll do.
I
They'll
couldn't
do-
see where your mouse was pointing at. I
Yeah,
don't know
you can
if
see
you
it
moved it
now,
or not.
right?
No.
Can you see it right now?
I can see it now.
It's small. Let me see. Let me see if I can annotate.
I don't know if mouse.
Okay, look at this. Check this out right here. I'm gonna circle it. Oh, it didn't let me circle. My Zoom controls have been a little strange today. I was able to pick up the pen, and I have the pen. No, I lost the pen. I'm able to pick up the pen. Yeah, so see that angle right there? On a porting, we could actually blend this in. Like we could maybe round the turn a little bit, maybe using our die grinder, you know, maybe kind of cut this down just a bit right here. Make it pretty nice. Yeah, the annotation's been a little tough today. So yeah, we might be able to clean that up with a porting job. But from the factory, again, you can see, let me get my mouse back here. You can see these 3 angles though, right? Now you can see it. I just have to get rid of that that drawing. I think it's being really weird. Let me test something really quick. Okay, so I got the annotate figured out. I don't have a good explanation for that. So my focus was explaining if air's coming in like this, like that, right? The more angles we get. So this has the 3 angles, so it's pretty smooth. But you can see like this one for sure has a fairly ugly corner. A 5 angle would take this corner down again, this corner down again, and this corner down again. It'd be more smooth. That'd be a lot more high performance. From the factory, though, you're not going to get a 5 angle. A 5 angle valve job is not happening from the factory. In a high performance, you could, and that'd be pretty cool. And then I know that you couldn't see for a little bit. So when I was talking about the Prussian blue, here you go. Slap it in there. And when I was talking about reading it, you'll notice this has a pretty nice even ring. Whereas let's just say it were to have a gap right here, you know, that would indicate either the valve is a little bent, or the valve has a little burn out of it, or a defect of some sort. And in that case, we need to evaluate that. Do we need to lap it and put the compound on there and spin it and basically just mate them together? Or maybe we need to cut a whole new seat and grind the valve. But either way, we need to get it to the point where we have a solid ring right in here. It needs to be all the way clean connection. If we don't, think about that. If you have an area where there's a space with no, let's say it's this one, you have no contact right here. What's that mean when we're on the compression stroke? It's not sealed. If it's not sealed, we're losing compression. If we're losing compression, we're losing power, potentially to the point of being able to cause a misfire. So if we have a misfire, now we're not passing smog, we're losing a lot of power, we're burning a lot of gas. It's a big problem.
Um,
Go ahead.
wouldn't you also be doing a cylinder leak down test to find out on faulty valves as well?
Exactly. So let's say, right? So a lot of times we're covering the concepts of the engine first, and actually we cover the diagnosis later. But this is a good example to help start sowing some seeds for that later time. If you would never just yank an engine apart and start checking this. It's not what you do. Now, if somebody dropped it off and said rebuild it, yeah, you should do this to be thorough, but that's not really how we do our job. What we would normally do is you get an engine and the engine's misfiring, right? You got to do some diagnosis. You think it might be spark. So you do a spark test and you're like, oh no, it does have spark. You think it might be fuel. So you do some testing on the injector of that. Let's say it's only misfiring on cylinder number 2. You test the spark on cylinder number 2. You test the injector on cylinder number 2. It's got spark. It's got fuel. You go ahead and you check compression because that would be the logical sequence. In fact, you might even argue that checking compression before fuel is easier, especially on a GDI. So either way, you got a misfire. You end up checking compression. Your 3 cylinders of your 4-cylinder make 175 psi, and then cylinder number 2 makes 100. That's your problem. They can be a little low altogether, but if you have a big difference like that, you have 175 on 3 of them, you only have 100 on 1, that cylinder's messed up. It's losing compression. Where's it losing compression? You don't know. You just know it's losing compression. The compression test gets you to that point where it's like, all right, I know it's in the cylinder. I just don't know what. Then we would do a cylinder leakage test, which would inject air into the cylinder. And let's just say that this one we were talking about right here is an intake valve. If you injected air in the cylinder and that valve was bent, damaged, defective, it had a problem with the seat, whatever, air would be leaking out right there. Where do you expect you would hear the air if you're doing the cylinder leakage listening? It's an intake valve. So you'd hear it actually coming out the air box. If you do a cylinder leakage test and you inject air in the cylinder and you hear air coming out the air box, you're like, boom, it's something up with the intake valve. The intake valve is not sealing. Then you may pull the head off. Then you may do this and be like, oh, okay, there's a big spot right there that's messed up. It needs the valve ground and new seats, or it needs a head or whatever. If you were to hear the air coming out the exhaust valve, you'd probably still want to do this to your intake valve, but actually we'd be over here. It'd be like, no, I'm focused on the exhaust valve because that's where my compression was leaking, as evident by my cylinder leakage test, something we cover in unit 6, I believe. So we're going to do extensive diagnosis, but this is a perfect point to help you start to understand kind of where we're going. There could be other air leaks, head gasket, that could be either to coolant. We could have leak to the crankcase, which would be more like bottom end. So there's still other stuff, but for valves, boom, you're at the perfect point to understand that. Cool. Now, speaking of head gaskets, we talked about that one yesterday. The customer engine had symptoms of a blown head gasket. It may very well be a blown head gasket. But when we inspect the head gasket, the head gasket may have blown because of a warped head. The head gasket may not be blown at all, but a warped head will give you the exact same symptoms. So when we're going to do this job, this picture shows you, your head surface should be flat. We're going to measure it diagonal. We're going to measure it top to bottom. We're going to measure it several different directions. And the whole time we're going to be trying to slide that feeler gauge in there. And if, you know, if the maximum warpage is 2000ths and it takes the feeler gauge, like the feeler gauge slides under that straight edge, that means there's inconsistencies, probably a warp of more than 2000ths. That head either needs to be resurfaced or replaced. If there's an inconsistent, like let's say there's a low spot right there and you can slide the feeler gauge. If there's a low spot of 2000ths, that means it's not clamping the head gasket down all the way. And you're going to have compression leak or coolant leak or oil leak or whatever you're going to have leak. A head gasket's not going to fix that, right? Because the head is not flat. The head can't properly squeeze and seal the head gasket. So anytime we're looking at head gasket work, we're also thoroughly inspecting for warpage, not only warpage, cracks, right? This could all give us symptoms of head gasket, even porosity. There's too much, but there's porosity in the casting. I mean, it can get a little tricky. We've seen a few vehicles over the years that are like, hey, we have this weird oil leak, and it wasn't a gasket, it wasn't a seal, it was actually porosity in the aluminum, right? So when we talk about a little bit of that stuff, if you look, we're not only measuring where the deck of the head is, where the head sits against the deck of the block, we're actually measuring the intake and exhaust manifold areas as well. If you're blowing out exhaust manifold gaskets, you may actually have a warped or wear on the surface where the exhaust manifold gasket sits, which again means the gasket's not being evenly and equally properly clamped, right? So there's a lot of inspection to do on the head to do it right. Those cracks, by the way, probably would be a replace for us. Some, shops, this is on a valve seat. Some shops may actually weld that and then remachine it, but in our area, that's a replace. You can see this one, but if you can't see it, that's when we do some of those dye testing. So you do the cleaner, do the penetrant dye, and then do the developer, and then clean it. And this would all clean up, and then you'd have a dark red or a dark blue, whatever color the dye is. It would really make that crack pop out. It would make it show a lot better. Like this one's a little harder to see. The dye would really help that. So that's why we do the dye test, the penetrant. And so typically there's about 3 steps. They tend to be similar, but they can vary. Now, and if you guys have any questions, don't put them in the chat. Just find a good spot to ask it. Okay, so I just check in the chat. I think we're pretty good. So let's just say you're going to go do this head work. You need to either just get new head bolts, and that's pretty standard. And on the ASE, if they say torque to yield bolts, they're cueing you, they're prompting you to say, hey, do you understand torque to yield bolts are one-time use? And I'm fine with that. And on some manufacturers, they just claim one-time use because we're torquing that bolt past its elasticity phase, and it's actually going to be stretched to the point of yielding. And that there's a good chance that that bolt is not going to return back to its original size. So for ASE terms, torque to yield, TTY, one-time use. But in reality, in service information, actually no. It says to measure the bolt. Sometimes it'll tell you to measure the length of the bolt. Sometimes it'll tell you, measure this distance out here, measure between these 2 points, measure between this line and this line, but you're actually going to measure it like this. Basically like this. You're going to measure it like how I'm showing you. Now, if you think about it, it's kind of like gum. If you're chewing, you take a piece of gum out and the gum's kind of thick, but let's say you stretch it, the gum gets thinner. So you can measure the stretch, not by the length, although you could in this one, you could also measure it by how thin it gets, like this in the middle. And so if your gum has gotten thin, you know it's stretched. If this bolt measurement right here is thin, that bolt is stretched. So it should be 10.85 to 11 is new, but the minimum is 1060 right here. If it's below 1060, replace the bolt. You know what a lot of techs are going to do? They're just going to be like, get new bolts. I'm not even playing around with measuring the bolts, but I'm just telling you, that's what service information calls out. That's not the only thing we got to measure for stretch. We got timing change. So timing chains can stretch. It's hard to measure an entire timing chain though. It's long. It's like, how are you going to actually measure that precisely? You don't have a caliper that's that big. So what they'll have you do, like in this example, this is one example, they'll have you look at measure 15 lengths, mark them out, and then measure the distance between the 15 pins. So it's actually not lengths, sorry, it's pins. 1, 2, 3, 4, 15. And the distance between 15 pins needs to be under 136.9. And you'd like to do that in several different points around the chain just to see if maybe one spot's stretched and another spot's not. If any of the spots are stretched beyond 136.9, then it's replace the chain. There's one other thing that this doesn't explain that I've more learned in my own ways that I think is fun. So I'm going to actually skip ahead and show you something that's not part of the curriculum at all. It's generally not real ASE based, but I want to show you. Look at this tensioner right here. This tensioner has a certain distance showing. If your chain is stretched, what do you think the effect would be on that tensioner? You guys think about your bicycles. You got a bicycle, and as the chain stretches,
It's loose.
yeah, it gets loose. Exactly. And if on a bike, you can slide the wheel back to tighten it back up. But in a timing chain, what would happen is this tensioner would extend itself further and further and further to make up for a stretched chain. So like good old flat rado, I'm actually going to look more at the tensioner to tell me if the chain is stretched. But the way the engineers would have you do it, you're going to basically get your fishing scale to measure how much your fish weighs, and you're going to stretch it with 33.1 foot-pounds, and then you're going to measure it with a maximum 136.9. Like this is a great test. This is kind of slow. I've already looked at the chain tensioner, and I've already got a very good idea of what I got. So I'm just giving you a little tip. All
I
right,
have
now
a question.
go ahead.
So doesn't that make the chain weaker though? Why would you want to extend the tensioner?
The tensioner extends itself because it's oil fed, but I'll acknowledge your point. Like it's not, hey, it's better to get a new chain, right? I agree. Hey, it's better to get a new chain, get a new tensioner. But by that logic, I would argue, why would you want to rebuild an engine then? Just get a new car, because then you got a new engine, new transmission, new everything. So some of this is like, I agree with you. It'd be better to replace it, but we're in the business of repairing it for the most cost-effective price without sacrificing reliability. So on one end of the spectrum, you say, just run the chain. It'll be all right. But you don't really know that. I don't really know that either. On the other end, you're like, replace it because it's better if everything's new. It's better if that thing's stretched, just do a new one. And I get both of those positions. But professionally, if something's in spec, we can use it because the engineers came up with the spec. The engineers study it. They know the materials. They know the metallurgy. They know the numbers. They know that's their area of expertise. An engineer does not need to be able to fix the car. That's not their skill set. That's our skill set. But the technician doesn't need to be able to say whether a part's good or bad based on their own feelings. They really just need to be able to compare it to service information and quantify it's good or it's bad based on the service manual. See what I'm saying? So of course, where my loyalty would be. I've never been an engineer. I spent a lot of years fixing a lot of crap. So like, I want to side with the tech, but the truth is the tech has no qualifications to say whether that chain's good or bad without comparing it to service information and seeing if it's stretched, right? And if it's stretched beyond a certain amount, then it's no good. And if it's stretched a little bit, but well within the range, then it's okay. And that's what you guys have to at least understand. Now, you can advise your customers really however you want, but if you were to get your butt hauled into court and you're saying, I'm following the manufacturer service information, I've measured it, I compared this number, you're looking really good. Whereas if you say, well, I've been a mechanic for 15 years and I've done this and this. And then they say, well, wait a minute, you have a manufacturer service information that said you have a maximum of 136.9. Did you measure it? And like, no. What the heck does the service manual know? You're going to jail or something. You're just going to look like an idiot. So it's my job to teach you a little bit of the by the book way, but also try to give you a little bit of wisdom and some perspective on why we do what we do. So yes, Roberto, I agree. Better to get a new chain. But if it's within spec, I ain't got nothing to say. It's in spec, it's in spec. I can use it. Cool. Now lifters. So if you're going to rebuild this engine, you're probably going to put some lifters in there. Lifters need to be essentially bled. So one of the ways we do this, we open up the lifters, we make a little tray of oil, we throw the lifters in there, and we leave them overnight. Another way we do it, you can actually get the lifter, you can get an SST, you could actually use a T-pin right here, or a paper clip, and you actually push the SST way down in there, and you depress the ball, and then you'd actually go in there and you'd pump it up while it's submerged in the oil, kind of like underwater, except it's not water, it's oil. All right, so that's how you prep them. What most people are going to do in the shop is throw those lifters in there, and slowly but surely the oil is going to go in and the air is going to bubble out. If you throw the lifters in, you'll start to see bubbles come out once in a while. So if it's a new lifter, you have to prime that. You have to get it ready. Cool. To check a lifter, if you grab a lifter out of the engine and you go ahead to pump it, you're going to try to press the plunger several times to see if the check ball's seated and if it's sealed. If you can compress it more than 3 times and it doesn't stiffen up, that lash adjuster is no good. So that lifter would be bad. That's how we check those. Now, commonly, right? And this is where it gets a little gray because I just lit you up about service info. Commonly, if you have a bad lifter, a lot of times what we'll tell the customers, hey, you should replace the set. And in service info, it's saying to pump it up. And if you can't pump it more than 3 times, then it's good. And that's true. I got no disagreement. However, if you're doing this and it's got a bunch of miles on it, you may want to say, hey, to the customer, look, you had a lifter fail. You got a bunch of miles on it. These lifters are checking out okay right now, but I don't know how much life they have. You may want to consider just spending the money on the other lifters because right now the labor's free because I already have it all apart. See? So I would agree with selling a set of lifters, but I would explain it very clearly to the customer. These lifters check out okay. I'm not telling you that you absolutely need lifters because these are bad. I'm telling you that it doesn't make a lot of sense to not replace these. And if you don't want to replace them, cool, I'll put it together. But if your lifter fails in another month, you're paying for this whole job and all this labor again. And the customer's gonna be like, well, that'd be stupid. Then cool. You were honest. That's the right way to do it. The wrong way would be like, you need all new lifters. All the lifters are bad because service information tells you how to check them if they're good or bad. Cool. So continuing, this talks a lot about valve seals. So intake side brown, exhaust side gray. Those colors are not universal, but just pointing out the exhaust valve gets much hotter. So they have a different type of seal on the exhaust valve than they do the intake valve. These are valve guide seals. These are the ones that can harden up and cause that oil consumption. It may very well be valve seals, exhaust valve guide seals. However, if you put new seals on and your valves were loose in the guide, there's excessive valve stem to valve guide clearance, you didn't fix it. Make sense? Now, when we drive them on, there's a lot of times an SST, we got to make sure it's on nice and square. If it's on crooked, it's obviously going to leak. There's also ways to do it in the car. And this used to be kind of common on the Lexus back in the day because people buy a Lexus, they didn't drive it that much. They were nice cars. So they're like, hey, I'm going to fix my oil consumption by doing valve guide seals because I don't have that many miles. So we wouldn't pull the head off and do a whole overhaul. We would literally have it in the car. So like this picture's how we do it, except it'd still be in the car. And there's a tool to actually bolt up and pry the valve spring down, pop the keepers out. But then if you pop the keepers out, isn't the valve going to fall in the cylinder? Yes. So first we do like a cylinder leakage tester and we'd inject air and pressurize the cylinder to over 100 PSI. And you could pop those keepers out and the valve would just stay up. The valve wouldn't fall down. You could take the spring off you could pull the valve guide seal off. You could put a new seal on. You could put the spring on, put the retainer on, and then use the tool to pry it back down and put the keepers back on. And you've got a new valve seal and you never had to pull the head. So that was a really cool procedure we were doing back in the day. But you'll notice at the end, they have you take a mallet and they have you slap the valve stem. When you slap the valve stem, that's going to actuate the valve. And if the keepers are messed up, that's going to give the keepers a chance to fly out, and then the keeper goes flying and the valve falls in. But better to do it now than to do it on the first startup and the valve drops inside the cylinder, gets smacked by the piston and totally grenades the engine. You know that's happened, and I was telling you guys about that. That's happened more than one occasion. So that's the reason that we go by and we slap it with a mallet. Not a really nasty metal hammer and try to mess the valve up, but just with the mallet would be good.
Like a dead blow, right?
Like a dead blow would be great. Perfect. Now, if you're working in the backyard and you want to get the keepers out, the other thing people would do is they'll take a socket that's like kind of the size of this tool. They'll put it on there and they'll just whack it with a hammer, and that would drive the retainer down, but not the valve. So the valve would hang up, the retainer would go down, and that would give the keepers a chance to pop out. It's a kind of a janky way to get the valves out. The better way is really just use the tool. But if you see somebody banging to get valves out, that's what they're doing. They're hitting a socket, which is going to loosen up the keeper for a quick second, and they'll fly out. It's not a real exact science. There's some backyard stuff there. Cool. And so now when we talk about the valve lash and stuff, I kind of already explained this. We're sliding a feeler gauge in. We're measuring that clearance. If that clearance is insufficient, that means it doesn't have enough of a gap. We have to open the gap up, which means we have to push the bucket down. But you can't push the bucket down because there's a shim right there. So you need to put a thinner shim in so the bucket can be pushed down a little bit more, right? And now you just have to do the math. I explained the math. I'm hoping that you guys got the math. I'll do one more. Okay, one more. That's it. I'm going to do even numbers. Your spec is 10. You're supposed to have 10 thousandths. Right now you have 5. If you want to get it back to 10, you'd have to slide this down 5. But to slide this down 5, you have to take 5 thousandths away from your shim. You can't take 5 thousandths out of your shim. You'd have to get a shim. You have to take your old shim, measure it, and then get a shim that's 5 thousandths thinner than that shim and put that one in. And that'll get us to drop down the 5 thousandths, which would restore your 10 thousandths optimum valve clearance. Cool. Could be shim, could be a selectable bucket, a bucket with a thickness. See, we're measuring the bucket from here to here, and this little beefy part is almost like a shim, except you can't replace it. It's built into the bucket. And they have buckets that have thicker or thinner right there. So we'd have to get the right bucket. And this would give you all the chart, and you can go in the tables and you can go into parts and you can get part numbers and all that type of stuff. But honestly, I don't spend a ton of time on it because I don't think you're actually going to do that. That's more going to be machine shop type of work. The machine shop probably won't even do that because, like I said, they're going to tip grind the valve or butt grind the valve. And then this one has the shim on the top. This was a better image of the shim on top, right? This is a better image of the shim on the bottom. The work is the same. The difficulty level is drastically different. So there's the two options. This out of a 3MZ, this out of a 2UZ. They were doing it different at different times. Now, if we're going to do that type of work, we may need to lock our timing sprockets. So like we're locking the cams because we're going to have to pull the cams out. So like if you could get a setup like this, and your timing belt, let's say in this case is off, but if you're able to keep your timing belt on or your timing chain on, and you could lock these, you could actually unbolt the sprocket, but leave the sprocket and take the cam kind of out the backside. That would be the quickest way to do the job. That's not always possible, but if it is, that's a way to pull the cams out without necessarily pulling the whole timing cover and all that type of stuff. Okay, now here's a basic timing chain. This one is out of a V8. The picture's actually upside down, but all we're doing is 1 mark to 1 mark. That's how an old small block Chevy was timed. It was very basic, very basic. And this has just a little tensioner shoe right there that's got a spring on it. It would just put a little pressure on it. That was it. We're way past that. So this is more the stuff that you guys have been seeing in class already. You got 2 timing chains. Sometimes you got 3 timing chains. Sometimes you got 4 timing chains. And they're going from here to this cam, back down. And then you got a double roller sprocket on the bottom. And they get a little bit intense. All right. But the point is, there's a couple points. If you follow the service manual and you understand all the marks and all the marks on the links and all that type of stuff, it's okay. You can do this. But I'll tell you the truth. The service manual doesn't explain it in a real easy to understand way. So that's part of the reason that we try to make videos. You're all going to do a timing chain on either a 4-cylinder, on a 6-cylinder, but you're also going to do a timing chain on the 3UR V8, the 5.7, and that is a beast. And if you can time that 5.7, I'm not worried about you out in the field. You're going to be just fine.
How about 3-cylinder?
I don't care about your 3-cylinder. No, if you can do the 3UR, you could do your little fancy race car. You could do your GR or whatever. So not a big deal. The 3-cylinders actually be the same as 4-cylinder. They get a little more complicated when they're V6, V8. Then it's like, well, you got 2 banks, right? So you got at least 2 chains. Sometimes they run 1 chain up to like a center shaft hub, and then they run 2 chains off of that. Like the 3UR runs a chain from the crank to the cam, but then a different chain from cam to cam. They're all over the place. They can be pretty intense. Now, what's it take to replace? It's a job. It's a job and a half. A lot of times you got to pull the oil pan to pull the timing cover. You got to pull the crankshaft sprocket to pull that. A lot of times you got to pull the valve cover. You're going to be deep in there. On some, like on a 2GR out of a Camry, drop the engine. Drop the engine just to do it. It's going to be, you're going to fight and struggle. I'm not even sure it's possible to do it without dropping the engine, to be honest with you. But even on some, you're going to fight and struggle to get all these bolts out of the timing cover and all this type of junk. It's going to be very, very difficult to do that without dropping the engine. Cool. And so yeah, I think we're probably pretty good. This is old school. So when you're talking with Grandpappy, then be like, oh yeah, I did the timing chain. Just look at this. That was the chain. It was a mark and a mark. And that was it right there. Pretty crazy. All right. And then if you look at the tensioner, like we talked about, this is oil fed. Okay. So this tensioner is not just like a spring or something. It gets oil from the lubrication system and it pumps it up and it pushes outward, and that gives the chain its tension. So if you have a problem with oil pressure, like you forgot to put oil in it, this isn't going to pump up. You're going to have all sorts of noises. One of the new noises is going to be timing chain noise. Now, what about a belt? This is Subaru Life, but this is actually one of the more complicated belts. Belts can be simple or belts can be complex, but chains generally don't need to be done. You're never going in to do a chain as a maintenance. Now, if the chain is stretched and you have an issue, you may need to go in there. If you're doing an engine rebuild, you should probably do the chain. But chains don't have like, change the timing chain at 60,000 miles. Now, somebody told me an exception on some Audi or something, but I didn't even verify that, but it could be true.
It is. So on certain early, I think early versions of the current gen 4-cylinder turbos, they would have timing chain tensioners and chain stretch issues. So yeah, that's kind of a thing with those guys.
But I'm curious if it's like, hey, it's a known issue. Because I mean, I could call out the GM 3.6 that's having a lot of timing chain issues too, but they don't have a like go in at 90,000 miles and replace it. They just say, hey, if you're getting this symptom, probably replace the chain. So
Yeah.
That's what I'm not too sure about.
Yeah, it's not really an interval. It's just a known issue.
Yeah. Okay. That makes a lot of sense. Known issues on chains. I agree with that. That happens. Service intervals, not sure that happens, but I don't know everything, and I'm more than happy to admit that. Timing belts, however, They have an interval. So you don't just do a timing belt when you're having a problem. That timing belt is due to be changed periodically. Maybe 5 years, 60,000 miles, maybe 90,000, seen as high as 105. But at that mileage, you're supposed to change the timing belt. If you don't, and it breaks, it was kind of your fault. See, so like I still have a brother-in-law. He's not speaking in your terms. He not like us. Okay. This is a white collar dude. He went to school. He's got, some degrees in business and, whatever. He has no interest in working on things. He asked, hey, what should I buy? I need to get a new car. I want it to be cheap. I don't want to spend a ton of money, whatever. I actually told him a Kia Soul, and I think it was good advice. It was a good car. It was cheap. I think he bought it new for like 12 grand, brand new with a warranty. It was like made a lot of sense. He drove the wheels off the thing, getting this business going and doing all these, meeting with customers, whatever. And then all of a sudden, boom, it broke down. So he brings it into the dealership and he's like, hey, this car broke. It's under warranty. It's got a 10-year, 100,000-mile warranty. And it's got like 70 something. I think it actually had more. I think it had more like 90,000. But it's got 90,000 miles. It's under warranty. And they're like, okay, we'll check it out. And they checked it out. And guess what happened? Timing belt broke. And then they're like, hey, we got some bad news. It's not under warranty. And he calls and he's like, what the heck? This car had a warranty and blah, blah, blah. And I said, yeah, it does. Don't even worry about it. You did all the maintenance, right? And he's like, yeah. And I said, and you were doing all the maintenance at the dealer like we talked about when you bought it? And he's like, well, the dealer's like 40 minutes away. And there's a guy who's in town who's like 20 minutes away. So I took it to him. And I was kind of like, uh-oh, here we go. And then I said, give me the paperwork. And the paperwork basically said the customer never changed the timing belt. The timing belt broke and nuked the engine. So I'm sorry, that's not warranty. And they're right, it's not. This timing belt is a maintenance item. You don't change this maintenance item, it causes a lot of damage. It potentially kills the engine. His pistons and valves hit, interference engine, done deal. They gave him a big estimate to replace the engine. And he's like, no way, I'm not going to do it. Was all upset. So I had to remind him, look, I told you take it to the dealer. The dealer's the one who's going to warranty it. If you've gone in there and you've done all your maintenance, you got nothing to worry about. But instead, you took it to the ding dong, to the mechanic downtown. He took it to the Midas Touch or something. And the Midas Touch was when he told him, hey, you were doing all my maintenance and, you've done all my oil changes and you sucked all the gravy off and you sold me the wallet flushes and you did like this flush and that flush and the other flush and you flushed everything out of my pockets, but you never told me to do a timing belt. And their answer was, well, we didn't know. We don't really do that. It's sort of like, dude, he trusted you guys to do the maintenance and you missed one of the biggest, most important maintenance items. It wasn't that important that he did the brake flush. It wasn't that important that he did the 3-part carbon cleaning for the top end carbon. You missed the timing belt and it ruined his engine and it's no longer under warranty. Okay. So that explains a lot about what you have to worry about with a timing belt. Any questions on that?
Not really a question, but kind of a story to reiterate why shops like Midas are terrible. I had a buddy who because I change oil for my friends on the side.
Sure.
And his last oil change was at Midas. And when I tried pulling the drain plug off, it was cranked to more foot-pounds than it should have been. Sure. And I noticed that the factory Toyota washer was crushed to the point where it was just smushed thin, like way thinner than it should be. And the little gasket was peeling off of it. And yeah, so I just say stay away from lube shops.
Pretty high quality service. So as far as what can happen with a timing belt, I think you get that. Now, another detail I'd like to say, if you notice, there's quite a bit of pulleys and stuff here. So if we're doing a timing belt, this is going to be a pretty big job. You got a crankshaft right here on this Subaru that has a seal. If that seal leaks, you got to pull this all apart and do the timing belt. So it may make sense to be like, hey, You need a timing belt. We might do the crankshaft seal. It'd be a good idea. Do you need it? It's not leaking right now, but if it leaks in 10,000 miles, we're going to have to do this whole job over. You got to pay it all over again, right? Same cam, crank, cam. There's 5 seals right there that we may at least want to give the customer the option to do. If it was my engine, I'd do the seals. If it was someone who has to pick between, do the timing belt and eat their food, or do the timing belt and the seals and go hungry, no, I'm going to say just do the belt. The belt's important. Now, there's more though. We've got idler pulleys. It might be a good idea to do those idler pulleys. And sometimes you can get a kit that comes with the pulleys that's actually cheaper than, like if you were to go buy the OEM belt, you might find who makes the OEM belt, Gates or Continental or something. And if you find who makes the OEM belt, they might have a kit where you can buy the belt and all these pulleys and potentially the tensioner for a pretty good deal. Then that's more like a timing belt kit. If you do the job and one of those pulleys makes noise, again, you got to do the job again. You could charge the customer. It's not unethical to charge the customer, but the customer's not being really well handled. And in a way, they're under our care. We need to care for them and say, hey, you might want to do these pulleys, because if you do the pulleys, then you don't have to worry about it for sure till the next time you need to do the timing belt, which might be 105,000 miles later. You may never do the timing belt again on this one. But that's not all. There's also big concern about the tensioner. The tensioner is probably something you should consider to do when you do the timing belt. At a minimum, I'm going to skip ahead. Look very carefully at the tensioner. This tensioner is just hydraulic pressurized and a lot of times a spring and sometimes charged with gas. If there's any dampness or leaking, you have to do the tensioner. These tensioners can fail. These tensioners with the spring, they're a little bit more like, yeah, you can pretty much see what's up. This tensioner spring, you could do the tensioner spring and do the tensioner. This also has a bearing because it's on the pulley. There's also an adjustment here. If you were to loosen that bolt and turn this with like an Allen key, it's eccentric. Notice the bolt's not in the center. You can actually swing the pulley up this way to get the belt to be a little bit tighter, in addition to the spring, kind of making the belt a little tighter. So there's some things to consider on the tensioner there. And last but not least, on that, there's a pulley here that we need to discuss. But rather than tell you all about the pulley, I'm going to once again use a parable to help you understand. I'm going to tell you a story that's going to help you understand a concept. I worked with my mentor. He was a Chevy guy. If you wanted him, like if you were in his little family, his circle of people that he was kind of taking care of with their cars, you bought a Silverado, you bought a Tahoe, you bought a Suburban, maybe a Trailblazer, but that was it. Those were your options. Well, he had a sister who's like, nah, I'm buying a Honda. And he's like, fine, you buy a Honda, no problem. But I'm not working on it. I don't work on those. I don't touch those. I'm not even going to remotely deal with that. So she bought a Honda and 60,000 came around and she needed a timing belt. So she took it to, I don't know, Monroe Brake Muffler or something. And they're like, yeah, you need a timing belt. They put the timing belt on. A month later, the water pump locked up and blew the timing belt off and blew the engine up. So like, what the heck? You just did the timing belt. And they're like, yeah, but your timing belt didn't fail. Your water pump is locked up. And she's like, oh man, that's horrible. Then of course, when she told my mentor, the mentor was like, see, I told you, the GMs, they don't have that type of stuff. But also it's a pretty known issue with professional technicians, or it's a pretty known, procedure. If you're going to do a timing belt and you're going to do the timing belt kit, usually we do water pump. So you guys have probably heard timing belt water pump kit. That's why. It's not to say the water pump needs to be done at 60. It's to say, if that water pump bearing locks up, it'll break the belt and it'll ruin your belt and it'll ruin your engine. So while you're in there, does the customer want to pay a little more money to get this water pump done? Because if they don't, and it seizes up like it did on this Honda Civic and it blows the belt off, it's kind of a bummer. So again, the customers are under our care. They didn't handle that one really well either. Additionally, the thing to think about is, hey, if your water pump is showing any signs of leaking, that's definitely the time to do it. Even if your water pump's not showing any signs of leaking, you may say, hey, your water pump can seize, your water pump can leak. Right now, we're going to charge you an hour and the cost of the water pump, or maybe even a half an hour. But if you don't do it, you're looking at 6 hours to do the timing belt plus an hour. You're going to pay 7 hours labor to do that. You want it for an hour while you may or may not need it, or do you want it for 7 hours later when you do need it, possibly, if that happens? All right, so we give them some good options. You can see it's under the cover. It's made of rubber, but there's more than rubber. There's a lot of times some sort of threading, Kevlar, you know, carbon fiber, all sorts of stuff in there to make that thing pretty strong. So they should last a long time, but they still do. They're going to fail. It's not if, it's a when. There's your tensioners like we talked about. Timing belt breaks. Look, these valves got hit, broke off, blue metal all over the place, damaged the head. That engine got fried. Now, talking about chains a little bit more. This is the 3UR timing chain thing. When you guys do this procedure, it talks about setting the cams up, but there's not necessarily marks. So like on a timing belt back here, there will be marks. Line this cam up here, line this cam up here, line this crank up here. There's marks and dots on this. So you're lining up all the marks, all the dots, and you're getting the belt on. And then you're going to make sure that it's tensioned, you know, and make sure you turn it 2 revolutions and make sure all the marks are still lined up after the 2 revolutions. That's it. You're good. Timing chains are very different. They still do the same function, but they do it in a weird way. So like sometimes timing chains are having you set the cams in certain spots, but there's not really a mark. So a lot of people came to me yesterday and they're like, how do we know it's at 55 degrees? And it was like, no, it's just approximate. Get it in that general area, because unlike a belt, we're not precisely lining up the cranking cam. A lot of times what we're doing marks. This orange link has to be lined up with this slot. If it's a little, like if the whole sprocket is turned a little clockwise, a little counterclockwise, doesn't really matter that much as long as this orange link is lined up with that slot. And on the back side of some of those, this yellow link with this line and this yellow link with this line. Now, on some of them, it's bank 1 is yellow link with one line, yellow link with one line, but bank 2 is, look at this, single dot, same line. It could also be, this one didn't show it great, but sometimes there's actually double lines. So this one actually showed it better. There's a single line there. See, there's a double line there. One bank might be the single line and the other bank might be the double line. It really varies. You have to follow service information very carefully, and it can be a little bit confusing, actually. So I do try to make videos on that to help. One thing on a belt, if we back up, boom, 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 boom. On a belt, if you're not exactly sure your marks, you can take the cover off and turn it over to make sure all your marks line up. And then be like, okay, I see all my marks. You could even use a little marker to highlight the marks and become very familiar with the marks so you know. With timing chains, it's tricky. These orange marks, these orange links, they might not line up every time. You might have to turn it 27 times to get them to line up. So a lot of times what we do, like this one will line up every time. But a lot of times what we'll do is we'll just basically yank it apart. You just got to know where it's going to go. You're going to pull it apart. And then when you go to put it together, you're going to make sure you have all the lines lined up. But setting it to top dead center and reviewing your marks and stuff, a lot of times we don't do that with chains. It just doesn't really work that way. Okay, so that's kind of normal. You can see sometimes the marks are like this. The mark is there, but also they give you another little window so you can kind of tell the mark is there. They're a little tricky. Here's your crankshaft. There's a mark to a mark. Again, we're not lining this mark up to a mark on the block. We're just literally doing this mark to this orange link. It's okay if it's over here as long as they're both over here. It's okay if it's over here as long as they're both over here because they're turning together. So it's just a different way to think about it. It's kind of interesting. Then one thing I show everybody really well is when you're going to put these on, you got to be really careful because you're trying to pop these sprockets on, which also have VVT. So some people would call it like a phaser. I've heard them called controllers. They've been called a number of different things. When you're trying to pop this on, there's a pin in the crank in the cam, and the pin has to go through a hole in the sprocket. And if it's not lined up and you try to run it in, you'll totally mess it up. You'll really screw that thing up bad. So you got to watch for that. There's some finesse right here. This wrench can hold or turn the cam because there's flats built into the cam. And then with this hand, you're kind of working it, getting into place. So I'm saying that was 55 degrees. It's not a real big deal. About 55. And then by the time you turn this, it's going to lock into place. And if these links are lined up, you're good. Even if it's at 54 or 57 or approximately 50 something, it's not a big deal. Cool. Hopefully that makes sense. Then we do the timing cover. Timing cover jobs can be a beast. You'll notice it's calling for 27 millimeters and 32 millimeters. And these are the bolt sizes. All those bolts are different sizes. You can try to reference this. By the time you get it all cleaned and prepped and all the gasket prep and you get the FIPG on there, which by the way, needs to have 3 to 4 millimeters, 2.5 millimeters from the cover. And then right here with the dashed line, it actually has to have extra. It has to have 6.4 millimeters, 7 millimeters from the edge. It needs to have different thicknesses of FIPG, form in place gasket, or RTV in different points. And then you only have like typically ASAP, but maybe 10 minutes, 15 minutes at the most to have that cover on, in place, not moving with the bolts in, and torqued is highly preferred. So you got like no time. You don't have time to be like, oh, the A bolts, those are 27.5 millimeters. There's one here, there's one here. What we recommend is you could actually take a piece of cardboard, trace this, poke a bunch of holes, and then poke the bolts where they go. And then if you poke the bolts where they go, then you're going to be able to pull them out of the hole and get them in place pretty quick. That would be the preferred method. Kind of makes sense? All right, so as we continue, you can see different bolts, different torques. It's kind of a hassle. And then we're going to do intro to VVT. Let me pause for a quick second. Okay, so VVT. There's a lot of different types. So we're going to cover several different ones, some of which will be Toyota, some of which will not be Toyota. And this is a little bit more to be generic. The ASE won't be asking you specific questions about BMW's Vanos or something. It's just going to be kind of general. So if we look at VVT, there's a couple things to point out. One, this whole assembly, they may call, like a lot of companies call it the phaser. Toyota will call it just a lot of times the sprocket. That's all they'll say. But this is the mechanism. So if you remember this one we were looking at, oops, gotta go forward, but my keyboard stopped working for some reason. Okay, let me undo my keyboard, redo my keyboard. Don't be like that to me. You are just mean. Okay, how about this? Okay, yeah, I can do touchscreen. We got this. So if you'll recall this is the phaser, but this is the cutaway. So when we're looking at this, what that looks like externally is like this. So that whole assembly has an external sprocket that's going to actually accept the chain. And then it also has an internal connection that's bolted to the cam. So what's weird to think about it is the two of them, they can actually move independently. You guys like the hybrid sound, huh? It's a familiar hybrid sound. Nice Corolla. Hopefully you can hear me good, okay? So we're going to keep rolling. So because they can move separately like this, if you see this center, this is the camshaft. And if you see the outside, this is the chain. So it's kind of weird, like VVT will keep the chain in the same spot, but it can actually move that center hub a little bit, which will change where the actual camshaft is. Okay, so that's how it's variable valve timing. The chain isn't moving, the chain's still lined up. When we set the timing chain, we're just lining the marks, the orange or yellow marks to the dots, we're good. Then oil will build up behind these little veins, and it'll actually push it clockwise for advanced, counterclockwise for retarded. Sorry about the terms. The terms are the terms. I don't make the terms. I just know the terms. All right. So backing it up, if you want to advance it, what we're going to do is we're going to take oil. We're going to send the oil into this solenoid, which a lot of times we'll call the OCV valve, oil control valve. And the oil is going to be waiting there, like ready to go. And then if we want it advanced, we'll actually duty cycle this, and we'll send oil through the passageway to the advanced side of this. So we'll send it in a hole right here, and it'll actually push this vein forward, and now it's advanced. Cool. Now, how do we do that? Well, computer controls that. You don't get to control it. The computer controls it. The computer references the sensor, so it knows the cam's position. That's an input to the ECM. The ECM is programmed, by the engineer to say, under this load at this temperature, let's advance the timing this amount, right? So typically under higher load and higher speeds, it's going to want more advanced timing. That's going to give us more power. But when the car's cold, we don't really want that. So it's going to reference like temperature. It's going to reference a whole bunch of stuff. And then let's say it sees everything it wants to give us 25 degrees of advanced timing, VVT. Then it would say, okay, 25 degrees, we're going to duty cycle that solenoid, let's say 40%, which is going to mean this is going to give out a square wave, 40% high, 60% low. That's going to pulse the solenoid, and that's going to control a volume of oil. That volume of oil is going to ultimately move this to the position we expect for 25 degrees of timing. The sensor is going to confirm it and be like, okay, yeah, you're at 45 there. Cool. Keep it right there. And it'll just keep that OCV valve pulsing the same duty cycle. Then if we want more advanced timing, because let's say you get ready to pass somebody, then it'll say, yeah, we want it more advanced. That would mean we need more oil flow. The ECM is kind of calculating and then saying, yeah, let's bump it up to 80% duty cycle. And then it's going to cycle it more, which means you're going to get more oil flow. Now, part of the reason, first off, that's a little bit engine performance, right? But part of the reason we bring it up like this is, take a look at this. That is all very dependent on the amount of oil, the viscosity of the oil, the condition of the oil. So I've seen a number of cars over the years that have come in with a check engine light, and the codes are variable valve timing or over advanced or something like that. And basically you think you need to troubleshoot the VVT system, and you're like looking at the ECM and the OCV and the, we need to check duty cycle. We need to bust out the pico scope. We need to look at whatever. Okay. Quite a few of them have just been low on oil. They forgot to do oil changes and it's sludgy. The oil's very dirty. Like, all those could be electrical issues, but they could also be oil problems. If the car calls for 0W20, you really need to be running 0W20. I know when 0W16 came out and they're like, oh yeah, you can use 0W20 one more time. Partially, it's because the VVT system is really sensitive. They know if you run that duty cycle 40%, they're expecting 25 degrees of timing advance, because they know how much oil it's going to flow and how much the oil is going to move these veins. You start changing your oil weight, all of a sudden it's like, hey, the VVT is not working how we expected. We did 40% duty cycle and we only got 10 degrees advanced. Let's set a code for the variable valve timing. Come to find out it's because somebody's like, well, my grandpappy told me you should run 10W30 no matter what, because it's mo better. Mo thicker is mo better. It's like, well, grandpappy couldn't even have dreamt of variable valve timing. So you don't have any real business doing anything other than what the service manual says. And if you do, and you can, but if you do, and you mess stuff up, you cause the problem. So if the customer uses different oil, if the technician working on it uses different oil, and it causes variable valve timing, that's no longer warranty. They mess that up. Could be just that simple, incorrect oil, right? But it could be other things. So these variable valve timing phasers, these vanes can wear, they can seize up, they can get debris in there. We've even seen some where they have a little knock pin, and the pin can have the whole oblong. Like we're gonna back up. I want to show you something right here. When we were about to look at these, this picture shows it. See, there's a hole right there and a little knock pin, like a roll pin type of thing, except it's solid. It's pretty strong. Has to go into that hole. We have seen where the technician misses the hole when they're about to install them like this, right here, misses the hole, sends the bolt in anyway, oblongs the knock pin. And now you have basically, rather than a round hole, you have an oblong hole. Well, think about that. If that hole is oblonged and it's anticipating it to be in a specific time, but it can wiggle on the cam, your variable valve timing is going to be affected. Your actual position sensor is going to be like, the timing is not where it's supposed to be. So it might not be oil, it might not be the solenoid, it might not be the wires, it might not be the duty cycle. It may literally be this technician missed the hole and now that's oblonged. So you may need to put a phaser, a sprocket on there. Okay, so the lesson there is, you get a code for something, you need to have an overall understanding of the system and all of its details to probably really be able to diagnose it, right? You can bust open service information. Service information is going to give you generally a good diagnostic flow. But like, if you zoom out and you're like, hey, I know so-and-so just did a timing cover on that one, and now it's got VVT issues, you might not waste any time checking your duty cycle. You might be like, yeah, they might have messed up that sprocket. They might have done whatever. Now, if you really wanted to be like mucho chingones, you could actually use your picoscope to scope out this cam sensor, and the other crank sensor, and see how they line up in phase. And you can actually tell if one of them's off. And if that hole was oblong, you'd actually notice maybe that cam is getting a little retarded and a little advanced when it shouldn't be. That might be an indication of one of those holes is oblong, right? So it's not to say that you should just blame the previous tech, but if you've got an indication based on knowing the service history, you might go about it in a way where you diagnose it quicker. Makes sense? But you can actually nail it down maybe with a Pico. You might also have to just do a tear down and evaluate it. But yeah, some good lessons there. Again, it's PCM's, ECM, whatever it is looking at all of these types of things. Right? There's a lot of inputs there. Now, Beamer does VVT, but Beamer doesn't call it VVT. They call it Vanos. Vanos is a German abbreviation of a variable Nacken Wellen Strungsbong Bing Bong 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 Sauerkraut.
Yeah.
Yeah, das Auto. So Vanos been doing it since 92. They had double Vanos, which means intake and exhaust. Toyota was actually doing just one as well, exhaust as well, first, and then they did VVTi. That's coming up. And then basically current models has something different. Double Vanos is variable valve timing on 2 cams, intake and exhaust, but Valvetronic is different. Nissan has it. They call it variable valve timing and lift, I believe. VVTEL, I think. So Valvetronic is actually more like a variable lobe. It's not when the valve opens, it's how far the valve opens. So this is kind of weird. VVT for most manufacturers is variable valve timing. For BMW, variable valve timing is known as Vanos. And then for a little while, BMW VVT was actually known as opening the valve more or not. They called it VVT, but they got away from that pretty quick, and now they call it Valvetronic, which that makes more sense. It was very confusing before. They'd be talking about VVT and you'd be thinking timing, and they'd be like, no, on a BMW, VVT is how far the valve opens. It's like, what is wrong with you? Something's seriously wrong with you. All right, and then Toyota VVT, variable with intelligence. So it used to only be the exhaust valve, and then they're like VVTi. Actually, I don't remember if it was the exhaust valve or the intake valve first, but it was one and not the other. And I think it was exhaust, but I'm a little fuzzy. So VVT was just one, and then VVT with intelligence. So VVTi means it's intake and exhaust. And that's pretty much, that's all you're going to see. Now it's going to be all intake and exhaust. We're doing so much. We're doing stuff with the EGR. Like it's all going to be both intake and exhaust cams now. Okay. And then there could be different VVTi, VVTIe, VVTLi. There's quite a few different ones. Nissan's, for example, CVTC is continuous variable valve timing. Everybody kind of copies each other, but they have to name it something different so that they're saying, oh, this is our proprietary version. We're not all just copying each other, I swear. Honda's is pretty different though. So again, they're all going after the same goal: create the best possible combustion event to decrease emissions to increase power. Pretty common. The Nissans, though, also use a progressive intake manifold. We're actually covering intakes in a little bit. Mercedes-Benz Camtronic, right? Again, another important note. It's very important that you're following the correct recommendation for oil from the OEM, from the original equipment manufacturer. Lack of maintenance. I mean, you're seeing it, not just my story, you're seeing it published. Sludging, gumming, old oil, thick oil, incorrect viscosity, all that can cause a lot of problems, right? So done now with VVT. You have a pretty big discussion on VVT though. It talks about all the different types, including showing you the animation of the VTEC, because VTEC is more than just VVT. It's actually different lobes. So it's kind of somewhere in between Vanos and Valvetronic, but combined, it's just different. All right, now we're into induction. So air filters, for example, Toyota uses basic air filters. Some manufacturers do what's called like a long life filtration system that can actually last 150,000 miles. So Ford, for example, is using this big old round cone, like lifetime basically filter. So there's some different examples. Here's another thing that you may see out there, so I want you to know. Sometimes they call this a filter minder, or in this case, air cleaner with filter service indicator. This is basically a little valve that has a spring. And if a vacuum is built up here, it will pop it to red. So you don't even, you can by all means pop the cover off and see if the filter's dirty. But if the filter is clogged enough to affect engine performance, this would show up red. You'd pop the hood and be like, why is that red? And then you'd press the end of it and it would go dong and you just reset it. But that's an indication, hey, this had an actual restriction. Now here's why. If you look at this top half, it goes to the engine, and the engine is the big sucker. It's trying to pull air in. The air filter should never be a restriction to how much air that pulls in. But if it is, it would actually draw this intake into a slight vacuum, which would lose power, by the way, but that would also set this. So if this gets some vacuum on it, bing, it goes to red. Okay, that's how those work. Pretty cool. Now talking about intakes. If we were to go back in the day, way back, you'd have the intake and exhaust on one side. So basically intake would come in, do its thing, and then exhaust would leave out the same side. So you had intake and exhaust manifolds on one side of the engine. It was kind of a mess. Cross flow head is just a very basic explanation for intake flows in on one side and exhaust flows out on the other. It's much more natural. It's going to get you better flow. Cross flow head has been everything for many, many years. This is normal, right? But they can design the intakes in many different ways. So we could say like, and in fact, I actually thought I had one more slide, but it looks like for some reason I must have accidentally deleted it. So what I'm going to do is pull up a quick search here, because I wanted to discuss the tumbler valve. So if we were to go like intake manifold tuning valve, we can discuss this a bit. So here we go. Let me pull this over. This is actually just the valve. So this valve is ECM controlled. You can understand the ECM can activate it, not activate it. I mean, here you got one actually for a Toyota. I believe that looks like a Toyota switching valve. So here's one that's a pretty good shot here. you can see this is not vacuum controlled. This one gets a connector from the ECM, and the ECM can either pull this rod in or push this rod out, right? So the DTC, for example, P2076, right, is just showing this is the valve. I had a couple pictures. I'm kind of annoyed that I deleted them. So that was my error, but it can set a code. And this one happens to be, I believe, on a Chevy Cruze apparently. But let's also go with a variable intake manifold. And we'll be able to explain it a bit better. Okay, for some reason that didn't search, did it? Okay, it did search. It was just slow. Let's go with this one. Actually looks pretty good. We're actually going to cheat off AutoZone. So on this system, if you'll notice, at lower RPMs, we want the air to come in the throttle body, and then we want it to go around the intake on long runners. Long runners. We want a long distance from the throttle body to the intake. That's good for low end grunt and torque, right? And in the past, you'd have to pick. You want long runners, you want short runners. And then we're like, well, you know what? I want both. Like, you can't have both, but I want it. And then somebody found out you can have both. So then they came up with this tuning valve. We're going to skip 2, right? But sometimes they can go 1, 2, and 3. We're just going to go 1 to 3. You had the long runners for torque. And then you know what? If you use the ECM to activate that valve, or you use the vacuum to activate that valve, it would actually close a door. And now the air comes in and it just takes the short path right to the cylinder. So you have a variable tuned intake. You have a long runner intake, or if you activate that valve, you have a short runner intake. So this one is great for torque, low speeds, and this one is perfect for high speeds. And you can have both as long as the ECM can control both. So sometimes Toyota would call it the tumble valve, the variable tuned intake valve. They'll call it all sorts of things. They're all very similar. On the side of the intake, you'll see something like that valve we saw, and that's what that valve does. Is that fairly simple enough? Not that complicated. Now, let's go with an old school throttle body. Let's just pick one that's cable, and I'm going to make this one a little bit bigger. You could go all the way back to carburetors, but you got to have a discussion on this, by the way, so don't panic. But here's a cool throttle body. You can see the cable goes to that, right? You guys know those are gone. So you understand it's been drive-by-wire for quite a while. So your cable no longer controls it. You're more looking at, like Continental actually makes quite a few of these. This one has no cable. It has a whole module here. And so when we're pressing on the accelerator pedal, we're really pushing on the accelerator pedal position sensor, sending an input to the ECM. ECM is doing some figuring, checking in with traction control and being like, hey, do you want to give it the beans, or are the rear tires already spinning? And it's like, yeah, give it the beans. And then ECM's like, all right, fine. Hey, throttle actuator, just run the motor, run it wide open, and it'll actually move the butterfly valve wide open. Like kind of we talked about that on the first unit 1, but just understanding these bolt to that intake, and the intake has the variable runners. Back in the day, especially with throttle body injection, our intakes were aluminum, and the aluminum intakes needed coolant to them. Some of the older throttle bodies needed coolant to them, but generally speaking, it's now plastic intakes and no coolant going to the throttle bodies. They've really been substantially simplified. Now, let me get that PowerPoint back up here. So probably pretty solid there. Now talk about exhaust. I didn't delete my exhaust pictures on accident, so that's good. Purpose of the exhaust: remove gases from the engine. It's basically get them away from the passenger compartment. So some people think it's cool cutting their mufflers off and whatever, and it sounds good, but this is the negative. Now your exhaust is not making it all the way out to the tailpipe. So you have the potential to have some carbon monoxide leaking into the engine, leaking into the cabin, the passenger compartment. So there's some issues there, right? But that's one of its jobs: reduce harmful emissions. You guys can imagine what part we're going to bring up when we talk about harmful emissions. Now here's your manifold, because we talked about manifolds on unit 1. The manifold's job is to bring either multiple ports down to 1, or in the case of the intake, 1 port into multiple ports, right? That's a manifold. So this is a good example of a manifold. This is an example of a manifold, but this is aftermarket and they're long tubes. So that would be like long tube header. That's a long tube header right now. That's aftermarket. This is actually a pretty nice header. That header is going to take up a lot of space, but you could pick up, 15, 20 horsepower potentially with that header if it's on, a V8 that breathes well minus the manifold. So headers can be cool. They do the same job as an exhaust manifold, but this is cast, not likely to crack because it's cast and it can handle more heat. These are good, but they tend to, flex and warp a little bit because they're kind of thin, and next thing you know, you got exhaust leaks. So headers are kind of hit and miss for me. Right. And then the muffler, it's obviously just to lower the decibels, lower in the sound. That's it. That's all it does. It's all it should do. If you cut your muffler off, did you gain power? Probably not. Any modern muffler is going to be good flowing, but still reduce the sound. Right. Exhaust pipes can be a number of different ways. They could be designed in a whole bunch of different ways. A flex pipe, you guys understand, is so that the engine can move around, the engine transmission can move around when the body doesn't. So we typically would have a flex pipe going to the engine because the engine would be moving. And then additionally, the whole exhaust is going to be probably held on brackets and hangers and rubber insulators and stuff. The exhaust makes a lot of vibration. If the exhaust is touching anywhere in the body, it's going to be a lot of noise, a lot of vibration, a lot. Sometimes it'll only do it when you're like in gear with your brake on, or if you rev it a little bit. Exhaust will make horrible noises. Heat shields that break loose will be tinny and rattling, clanking all over. They can make horrible noises. Once you get a few exhaust noises and you hear them, you'll be pretty good at being like, oh, I know what that is. That's a heat shield. Let me look for a heat shield. Or, oh, I know what that is. That exhaust must have a broken hanger and it's banging up against the frame or the body. You get you get a feel for it, right? Catalytic converter, do you guys actually know what this does? This, we got to cover a little bit more because it can be on this one. You're going to cover it a bit more in A8, in engine performance. So it reduces emissions, right? Does anybody know how?
I know that it has certain metals in it that effectively tries to add more oxygen to the carbon monoxide to convert a good chunk of the monoxide to dioxide.
Yeah, and I won't focus a lot on the particular elements, but I'm gonna say overall, like some people think it's an incinerator, like it gets so hot it just burns everything. That's not exactly true. The term catalyst is a chemical reaction. So they do have particular metals and materials that, when heated to the correct temperature, will interact with our engine's normal emissions, like you're saying, hydrocarbons, carbon monoxide, oxides of nitrogen, right? It's going to take those and exactly all the elements in the catalytic converter. To be honest, I don't really know. Rhodium, palladium, expensive stuff. That's why they're being stolen and melted down and sold back, right? But it's going to basically induce this chemical reaction where your hydrocarbons are going to be reduced. It's got a three-way catalyst, so your oxides of nitrogen are going to be reduced. Carbon monoxide should be reduced to carbon dioxide and water, because there's hydrogen. It'll pull a molecule off and it'll combine the molecule to become water. So it's completely normal to have drips of water coming out of the exhaust, because that's how the catalyst works. The catalyst is a chemical catalyst. It makes certain gases into different gases and water. So it's totally normal. Some of the importances for you would be if we have an engine that consumes oil, it's got worn rings, it's got worn valve seals, it's got loose valve guides, it's got scoring in the cylinder, it's got out of round, it's got X, Y, and Z. Oil will pass through the rings and or valves and go into the exhaust, and that oil will coat the catalyst. All those chemicals we talked about that are in the catalyst will now just be coated with a layer like sooty oil and will no longer get the cleaning effect on our hydrocarbons, carbon monoxide, and oxides of nitrogen. And the car will fail smog. And basically the cat will be destroyed. So here's a saying for you. It's a disturbing one. Cats don't die. They're murdered. What we mean by that, it's disturbing. We're talking about catalytic converters. Catalytic converters don't just be like, yeah, I just give up. They are damaged. They may very well be damaged by oil consumption. So oil consumption is not quite as simple as, oh, well, I just need to make sure I keep oil in it, otherwise it's going to seize up. It's like oil consumption. You're killing the catalytic converters. That car's not going to pass smog unless you keep putting new cats on it all the time. And even then, it still might not pass smog, because if you can see visual smoke when you rev it, that's a fail. So, I mean, our engine is the instigator for failing smog, for having high emissions, for damaging the cat, these types of things. Right? If our engine's in good shape, our cat should be able to handle it. If your engine's got a lot of miles and it's consuming oil, I'm sorry, it just is what it is. Your catalytic converter is going to be damaged. Similar with a misfire. If you get a misfire and it's shooting raw fuel in the exhaust, that's going to melt the cat down. It could do it in a week. It could do it fast. It can totally kill it. And they're very expensive, so that's part of the thing with the cat. Now, when we're doing our exhaust work, our engine work, if you pull an exhaust part, like you unbolt a pipe, you unbolt the manifold, you unbolt the cat, whatever, these gaskets are really meant to be replaced. Now, if we're in lab and we're practicing, cool. But if it's a customer job and you need to pull the engine and put it back in, if you separate the exhaust, you're going to need gaskets wherever you separated it. Could you get away with it? Maybe. But if it leaks, you got no one to blame. By the book, you're supposed to replace gaskets anytime you unbolt two parts. Okay, so now you know. A donut's kind of similar. Donut's a little bit more forgiving. If your exhaust is not perfectly aligned, the donut kind of gives it a little bit of wiggle room to change angles and stuff. But the donut's nothing more than a really thick exhaust gasket that's kind of like on a ball and socket. So in case your pipe is just a little off, you could still seal it up. They're pretty cool. Now you're ready for something fun. Let's talk about turbochargers, because that's what we need to cover. So turbocharger, first off, why do we have them? Well, look at this. Volumetric efficiency. We're always trying to hit that 100%. But if we can build boost and we can pressurize this cylinder, we can go higher than 100% volumetric efficiency, like potentially 150. So if we can make 150% volumetric efficiency, we are making more power with less displacement. Make sense? So if you had a 3-liter V6 at less than 100% efficiency, and you swapped it out to a 2-liter 4-cylinder with 150% volumetric efficiency, the 4-cylinder is going to make more power. 4-cylinders to make more torque. So the purpose of a turbocharger is to add power, but not just in a sloppy way. They actually make the engine more efficient. They do, genuinely. Especially because when we back up here, what's driving the turbocharger? Well, we've got exhaust gases flowing out the tailpipe, as you can see. The engine pumps, the exhaust stroke, it goes through the manifold. We force it through the turbo, please hold, and then we send it through a resonator, past O2 sensors, through the tailpipe, right, through a cat, through all that stuff. That exhaust gas is already leaving. That exhaust vent gas, we do nothing with that stuff. We just let it go. Just let it go. Let it go. So what if we take that exhaust gas that's already flowing and we capture its energy by putting a turbine in the manifold and forcing the exhaust to spin the turbine before it leaves? We're not really hurting the engine. We may add a little bit of back pressure, but we're not really robbing the engine of any power. We're just taking advantage of what was going by anyway, right? Then what we're going to do, we're going to take that turbine and put it in a housing. We're going to put that turbine onto a shaft and have that shaft have another wheel on it, but we're going to call it an impeller. They might sometimes call it the compressor wheel, But if it's got an impeller, the impeller is being spun by the shaft, which is being spun by the turbine, which is being driven by the exhaust gas, right? So it's efficient. The impeller is going to basically take fresh air. Fresh air is going to come in, go through a filter, go through some ducting, go through, maybe there's a little resonator, there's little boxes on there to make it quiet. And then it's going to go into the turbo, and the impeller is going to be like, yeah, give me more. I'm spinning. It's going to suck it in. It's going to actually compress it depending on the turbocharger's actual speed. And then it's going to send it here. There's one problem though. When you compress air, you had less air and you packed it, you had more air and you packed it into a tighter space. There's more molecules in that space. You just heated it up. So you had nice cool air and now you have hot air. And it's sort of like, yeah, you have more hot air. You have more, but like it'd be better if the air was cool, right? Because then it could be more dense. So we send it through an intercooler. The intercooler could be air to air, could be liquid. So if it's air to air, that's something that's probably going to hang down the front bumper, and the air flowing through the bumper grill is going to cool the intercooler, and the intercooler metal is going to cool the charge air, the boost pressure, the boost air. Or it could be like Subaru. You pop the hood and it's got this tiny little intercooler, but it's got coolant going to it. So if we run, and some of them actually have two cooling systems, but if we run cooler coolant and the coolant is cooler than the hot compressed air in the intercooler, the coolant will actually cool it too. So, and it'll cool it at about a 4-to-1 ratio. So if you have an intercooler that's liquid cooled, it can cool 4 times as effectively, assuming the air and the coolant temperature are the same. So if it doesn't have a standalone cooling system, that coolant's not going to be that cool. It's not going to work as well. But some of them have a totally separate cooling system that doesn't cool the engine. It only cools the intercooler, right? So this could go like, you could go way in detail. But basically, after we cool it, we send it into the engine and it's pressurized, and that's how we exceed 150% volumetric efficiency. Now we got to go a little bit more into the turbo here. So the turbo is taking advantage of the kinetic energy that's already leaving. It's going through the hot side, which is the turbine. It makes the shaft turn. In the center, we have bearings, and those bearings need to be well lubricated. The turbocharger can spin so fast. We got to have clean oil. We got to have correct oil. It's got to be well supplied, right? So it puts a little bit more strain on the lubrication system having to cool and lube a turbo. And then this is the cold air side. Air is going to come in, be pressurized, and come out as boost depending on the pressure. But we have to be able to control that. So that's one of the things this talks about. Using waste gates, exactly how we're going to do that. We don't want to make too much pressure, etc. So if you look like this is an example of a waste gate. So if you have a waste gate, it's going to essentially, in fact, this one probably shows it better in action. I don't know if I can zoom though. And by the way, this one is kind of weird because yes, it has a supercharger and a turbocharger, which is cool, but skip that for now. Yeah, I can zoom in. Cool, dude. So look, exhaust gas comes down here. Exhaust gas is going to spin up that turbine. However, if the turbine is spinning too fast, it can make an overboost condition, too much boost pressure. So what we can do is, using a waste gate, we could basically close a little valve or open a little valve. Actually, it's more likely open. If we open a little valve, the exhaust is like, why go through this turbine? I can just go right here and I can essentially kind of like go around the turbo and just easily escape, right? So if we close the wastegate, we force it through the turbine. If we open a wastegate, we give it a path around there. If your turbine is spinning too fast, it would know that because your map sensor will be like, hey, you're making too much boost, chill out. It'd send a signal and be like, yeah, open up the wastegate. The wastegate is the bypass. That's going to slow the turbine down. That's going to reduce our boost pressure. You get kind of an idea of how wastegates work. If it was old school, the wastegate would actually have a vacuum line go into it. And under vacuum, it'd be like, yeah, close the wastegate. We need more boost. And then let's just say that that wastegate was like pre-set up with a spring to 15 PSI, which would be pretty cool. 15 PSI hits, all of a sudden that 15 PSI pushes the spring on the wastegate, and the wastegate's like, oh, yeah, open up, boom, and it just opens. Now, it does it in a little bit of a weird way because the wastegate is a bypass. It just slows the turbine down. Most of the new stuff is going to be electronically controlled. It has an electronic wastegate, which I believe we had shown. Just got to zoom out because it thinks I'm trying to move. This one, it doesn't really show it all that well, but a lot of the new turbos, like on the twin turbo V6 Tundra, electronic wastegate. That's all computer controlled. Computer looks at the sensor. Computer says, open the wastegate, close the wastegate, all on demand. It can keep the boost up pretty good though. Those are pretty nice. But there's one more that it talked about. Talk about the blow-off valve. And what the heck is a blow-off valve? Blow-off valve is generally not something that a manufacturer puts on the car from factory. However, the blow-off valve, if the blow-off valve will be installed in the intake, so we back up. Blow-off valve could be installed on the intake, which is, I forget which one it was, if it was even on here. Well, you know what? I'd use a different one, turbo recirculation valve. I could help you with that. So the blow-off valve, if it's a true blow-off valve, let's say we set that at 20 PSI. If you're going and you shift, all of a sudden, you had your RPMs way up, your turbine was spinning really fast, and then you shift up a gear. Now your engine's moving slower. There's more than enough volume of air to really keep that thing at boost. You'll build excessive boost right then and there. The blow-off valve will be like, oh, if I hit 20 PSI, my spring will allow that air to blow out. And you get a whoosh, it sounds pretty cool. That's a blow-off valve. That's because you shifted, dropped the RPM down, but the turbine was still spinning fast, and we just basically dumped the air out the intake. Right? From the factory, they don't do that. They do a recirculation valve. They'll pull the boost pressure from like basically the excess pressure, and they'll just like dump it back off into the intake. So that way it's quieter. It's not quite as cool. Make sense? Roberto, I see your hand.
What happens if the wastegate valve stays stuck closed or open?
It's a great point. So if we're good on the blow-off valve, that's aftermarket stuff. They may have one on the manufacturer, but they'll probably call it actually a turbo air recirculation valve. That just bleeds off excess pressure back into the intake stream. Cool. Now let's go back to this wastegate. All right. If this wastegate was stuck open, what's the air doing? What's the exhaust doing? Is it spinning the turbine, or what's it doing? If this valve right here is
Constantly leaving?
So it's bypassing it. So that means the turbine's not being spun up, which means you're not going to make a lot of boost pressure. You need to be under boost. You get a code. It's actually under boost. It'll be like, this car has no power. It's not really running that strong. And that's because your wastegate's stuck open. So you could do some troubleshooting, wastegate stuck open. Now let's say the other way. The wastegate, which is the trap door, is stuck closed. What do you think would happen? Anybody?
Overboost?
Exactly. If your wastegate is stuck closed and your turbine spins up too fast and it's making too much boost, and then your wastegate's like, yeah, let me dump it, but it's stuck. It's like, you ain't dumping nothing. Boost more, and overboost. Both of those will set codes. So from a manufacturer standpoint, those are DTCs that are set. When those codes get set, car fails smog, you get a check engine light, etc. Now, race car stuff, especially if it's, let's say, here we go, the just straight up mechanical wastegate, which I didn't mean to click quite that far. That's not going to set a check engine light. There's nothing that monitors that. But if you're over boosting, that's dangerous. That's when you can have some engine, issues. So the mechanical wastegates were fairly reliable, but at least with an electronic one, if it does mess up, you get a code that's set. So it over boosted. Otherwise, you got to be watching your gauges and making sure you're not going up above whatever your number is. Cool thing with the mechanicals, though, if you want to increase or decrease, a lot of times these have an adjustment, like an Allen screw. You can increase the boost pressure or decrease it just by turning with an Allen wrench. Cool. Roberto, any more questions? You feel good.
Oh, good.
So blow off valves and wastegates are like completely different.
Correct. So in summary, the wastegate lowers or raises the speed of the turbine, which controls boost like the legitimate way, right? The blow off valve is really just there to blow off extra boost. It shouldn't really be needed, except when you do a shift, the wastegate will be like, whoa, slow it down. But the turbo already made the boost pressure, right? So the boost pressure is already there. The wastegate's just to bleed off excessive. The blow off valve is just to bleed off excessive. The wastegate is there to really manage the boost pressure. The wastegate is the main workhorse. Kind of makes sense. And then again, factory cars don't have a blow off valve. Factory cars will use this turbo air recirculation valve. It's actually just like a blow off valve, except rather than venting it to atmosphere and going, it's going to basically vent it back into the intake stream. It's just going to be like, and you didn't even know. Cool for sound. Okay, you like it? Love it. You want some more of it. All right, so there you go. There's your BOV. Cool, dude. Now, supercharger. Very different. And later, you guys are gonna get the chance to go to SEMA, so we can be like, yeah, you come back, you do some research. Somebody will likely do a presentation on turbochargers. Somebody will likely do one on superchargers. Then we can all vote, what's your favorite? The main difference, a supercharger takes power to make power. So the supercharger, as you can see, has a big old snout right here and is driven by the belt. Now, there's positives and negatives, right? The turbocharger is driven by exhaust gases, which is more efficient, but at idle, you don't have a lot of exhaust gases, so you have a big lag right there. Whereas the supercharger is like, it's driven by the engine, by the belt, so it's like, oh, you want boost now? I give you boost now. So there's no delay on a supercharger. But again, it takes power to make power. It's just at a good ratio. It's kind of like going to school and getting trained. It takes money, it takes time, but you're going to spend, $4,000 to do this entire program, and then you're going to make way more than 4,000 back. So if this supercharger takes 50 horsepower, but it gives us an extra 150, it's a good deal. With that being said, though, that's for horsepower. For efficiency, yeah, now you're having to turn more parts than you used to have to turn. Superchargers are not generally for efficiency. The only way they'd be for efficiency is if you had like, hey, we're going to do a really tiny engine, but we're going to supercharge it. So that way you don't need a big engine. But even then, I'm not sure that you're really improving anything, right? So like adding a supercharger is never going to give you gas mileage. Turbos are interesting. If you do a really nice tight build that's clean, you could do a turbocharger and not get worse gas mileage while you're really taking it easy. Now, as soon as you get into it and that turbo spools, you're going to burn way more gas. So it's kind of hit and miss. And basically the turbocharger or the supercharger, belt driven. Now let's back up to this diagram. It's belt driven right here. Air comes into it through the air cleaner, and the supercharger is basically sucking air through the intake and pressurizing it through the charge tubing, and then it would actually go right into the engine. So you can see pressurizing it, and then it would go like this, boom, right into the engine. They may or may not have intercoolers. A nice supercharger would probably have an intercooler. This factory one on a 3.8 liter, these didn't have intercoolers. These made I think like 50 horsepower more than the non-supercharged version. It wasn't really that big of a thing. Some of the TRD superchargers are kind of similar. You might get 50 horsepower, you might get 75. If you wanted to go real wild, you'd get like a VTEC centrifugal driven supercharger and a big intercooler and like boost it to the moon. You can make big power, but they just really vary. So kind of tough to say. The newer stuff that's doing supercharger, our Camaro, for example, has got a supercharger that's driven pretty strong. It adds a lot of power, like another 200 horsepower. But it's also got a liquid intercooler, and it's got a full standalone cooling system. So it's got an electric water pump that pumps coolant out to a radiator for the supercharger and into the intercooler for the supercharger. And overall, it cools the air down quite a bit. So they can vary. They can be like a basic one like this, or they could be like a full-on, big supercharger with an added belt with cooling and intercoolers and all sorts of stuff. It just really varies. All right, so both of those are kind of similar. Now, as for diagnosing, let's jump back on the turbo. This turbo has seals right here. So if those seals, and basically what they seal is in the middle, there's rotating parts, and the turbocharger has bearings, and in the middle there's oil to lubricate the bearings. On this side, there's intake air. On this side, there's exhaust air. Exhaust air is being pushed in. So generally, we don't have really typically all that much oil really passing through there. A lot of times we'd have oil getting pulled into the intake stream. But if those seals fail, we end up with oil not in the center lubricating. The center section, sometimes they'll call it like a center housing rotating assembly. It would actually get it into the airstream, and now you have a turbocharger that's pumping oil into your intake or exhaust, but probably intake, and it's burning a ton of oil. So turbochargers can be the source of oil consumption, can and have been many times. Other thing is, if your turbocharger, if you're working it pretty hard, they can add a whole lot of heat to your engine, to your oil. So some people will do like turbo timers, so somebody might do a presentation on turbo timer. It's not exactly an ASE concept. However, some manufacturers will say, if you're driving your turbocharged car hard and you just, did a pull and let it idle for 1 to 5 minutes before shutting off, because we're trying to really cool those bearings down. Additionally, if the turbocharger does have a failure, let's say one of those bearings gets messed up and it seizes up and you break off the impeller, that impeller's in the intake stream, that impeller may go into your engine and nuke the engine. So some would argue that turbochargers need more maintenance. You definitely got to watch those oil change intervals. You're definitely not going to want to be going over on those. They're going to be less forgiving. The turbo bearings spin really fast and they really need clean oil. Okay, now compared to like a supercharger, so superchargers can be a little tricky. Supercharger have the same risk. If any of the supercharger parts break and they end up in the engine, you're grenaded. But remember, the supercharger's belt driven. So you could have a problem with the belt where the belt will slip under load. There's some different types of situations where that belt could slip. That could cause an underboost. So you might be looking at the belt to diagnose what you think is a supercharger issue. The turbocharger, for example, like if it's underboost or overboost, we're pretty much looking at the wastegate, and so either of those, they can vary. Like some superchargers are fed by engine oil from the oil pump. Almost all, if not all, turbochargers are. But there are other superchargers, like this one, that actually don't get any engine oil. They have their own oil. There's a fill plug and a drain plug, and you actually have to change that supercharger oil on a maintenance periodically. I believe that's how the TRDs are too. So kind of different. They really vary. And with that is your entire induction and top end and head and valves and all sorts of stuff. Okay, so how you guys feeling? Think you're ready?